Hello there, and welcome to Science for Sleep, where curiosity gets comfortable, science takes its time, and the universe becomes a little easier to explore with your eyes closed. Tonight, we're setting out on a journey across some of the largest structures that exist anywhere in the cosmos. Not planets, not stars, and not even solar systems. We're talking about galaxies. Vast collections of stars, gas, dust, dark matter, and mysteries, all gathered together across distances so enormous that even light, the fastest thing we know of, needs thousands and millions, or sometimes hundreds of millions of years to travel from one side to the other. Before we begin, I'd love to ask you something. Where are you listening from tonight? Are you relaxing at home after a long day? Sitting by a window while the world outside grows quiet? Perhaps you're listening from a city filled with lights, or from somewhere rural where the stars still manage to put on a proper show. And while you're thinking about that, here's another question. If you could somehow leave Earth right now and travel across the universe, what kind of galaxy would you hope to visit first? Would you choose one that looks elegant and orderly, with graceful spiral arms wrapping around a brilliant center? Would you prefer something strange and chaotic, where stars are forming in unexpected places and the entire structure seems to ignore the usual rules? Or perhaps you'd be curious about the giants, the galaxies so enormous that our own Milky Way would seem modest by comparison. It's a difficult choice, especially since every galaxy has a personality of its own. If you find this little voyage relaxing, interesting, or simply a pleasant way to wind down before sleep, I'd be grateful if you gave the video a like and maybe subscribed as well. It helps this cozy corner of science reach more curious travelers who might enjoy drifting through the universe one gentle topic at a time. Now get comfortable, settle into your favourite position, let your shoulders relax, allow the day to slowly fade into the background. Because tonight we're going to visit every major type of galaxy known to science, from elegant spirals to giant ellipticals, from tiny dwarfs to cosmic collisions so dramatic they can completely reshape entire star systems. And perhaps the most surprising part of all is that galaxies are not merely collections of stars. They are histories, they are records. Each one tells a story stretching back billions of years. In a way, every galaxy is a cosmic city carrying the memory of everything that has happened inside it. The story begins with a simple question. What exactly is a galaxy? At first glance, the answer seems straightforward. A galaxy is a huge collection of stars held together by gravity. Simple enough. But as is often the case in astronomy, the simple answer only opens the door to a much larger one. Let's imagine for a moment that you're standing outside on a clear night. Above you stretches the sky. You can see a few bright stars, perhaps a planet or two. If you're lucky enough to be somewhere dark, you might even see the faint band of the Milky Way stretching overhead. Those stars may appear close together from our perspective, but they're actually separated by astonishing distances. The nearest star beyond our Sun, a star called Proxima Centauri, is more than 4 light-years away. If you could travel at the speed of a modern passenger airplane, reaching it would take millions of years. And yet, despite those vast separations, stars rarely exist completely alone. Gravity has a habit of gathering things together. Planets gather around stars, moons gather around planets, stars gather into groups, and on the largest scales, enormous populations of stars gather into galaxies. Our own home galaxy, the Milky Way, contains somewhere between 100 billion and 400 billion stars. Even that number is difficult to imagine. Suppose you counted one star every second, not every day, not every minute, every single second, without sleeping, without taking breaks, without stopping for food. To count 100 billion stars would still take thousands of years, and yet the Milky Way is only one galaxy among many. Astronomers estimate that the observable universe contains hundreds of billions, and perhaps even trillions of galaxies, each filled with stars, each following its own evolutionary path, each shaped by gravity, collisions, star formation, and time. It's rather humbling when you think about it. Human beings often feel large within their daily lives. We build cities, we cross oceans, we launch spacecraft, we create technologies that would have seemed magical only a few generations ago. Yet our entire civilization exists within a tiny corner of a single planet, orbiting a single star inside a single galaxy. And that galaxy is only one resident in a universe crowded beyond imagination. Of course, astronomers haven't spent centuries studying galaxies simply because they're large. Size alone isn't what makes them fascinating. What makes galaxies remarkable is their variety. For a long time, scientists assumed galaxies might all be roughly similar, different sizes perhaps, different ages, but fundamentally the same. Then telescopes improved, observations multiplied, photographs accumulated, and astronomers began noticing something unexpected. Galaxies come in many different forms. Some are graceful and symmetrical, others look distorted and chaotic. Some are packed with young blue stars, others contain mostly old red ones. Some actively create stars at astonishing rates, others have become quiet and relatively inactive. Imagine arriving in a country you've never visited before. You expect every city to look more or less alike. Instead, you discover enormous differences. Some cities are built around rivers, others around mountains. Some are ancient, others are modern. Some are crowded and energetic, others are calm and quiet. Galaxies turned out to be much the same. No two are exactly alike. Yet patterns began emerging. Certain shapes appeared again and again. Certain structures repeated themselves across the cosmos. Eventually, astronomers realized they could organize galaxies into broad categories, not because nature loves neat labels, but because those labels help reveal how galaxies form and change over time. One of the most important figures in this effort was a young astronomer named Edwin Hubble. Today, many people know his name because of the famous space telescope that bears it. Long before that telescope existed, however, Hubble was helping transform our understanding of the universe. In the early 20th century, astronomy was undergoing a revolution. For centuries, people had debated the nature of faint spiral clouds visible through telescopes. Were they part of the Milky Way? Or were they something else entirely? The answer turned out to be extraordinary. Those faint clouds were not nearby objects. They were entire galaxies, island universes, immense star systems located far beyond our own. Once astronomers understood this, the universe suddenly became far larger than anyone had imagined. It's a bit like discovering that what you thought were distant ships on the horizon are actually entire continents. Everything expands at once. Your sense of scale changes immediately. Hubble didn't just help establish the existence of other galaxies. He also noticed that many galaxies could be grouped according to their appearance. Some possessed beautiful spiral arms. Others appeared smooth and rounded. Still others seemed irregular and difficult to classify. These observations eventually led to one of the most famous organizational systems in astronomy, a framework that remains influential even today. Now, before we dive into the individual galaxy types throughout our journey, it's worth appreciating just how challenging this work can be. Classifying galaxies sounds simple enough. You point a telescope, you take a photograph, you decide what you're looking at, but galaxies are enormous, distant and often messy. Some are tilted at awkward angles, some are partially obscured by dust, others are actively colliding with neighbouring galaxies. Imagine trying to categorize thousands of cities while viewing them from an airplane flying at high altitude. You might mistake a harbour for a river, a stadium for a factory, a highway for a railway line. Perspective matters. Astronomers face similar challenges every day. Yet despite these difficulties, clear categories emerged, and those categories revealed something profound. Galaxies are not static objects. They change. A galaxy observed today is merely a snapshot in a story billions of years long. Stars are born. Stars die. Gas clouds collapse. Black holes grow. Galaxies merge. Structures evolve. Over immense spans of time, one type of galaxy can transform into another. That's one reason this topic is so fascinating. We're not simply looking at different kinds of objects, we're observing different stages of cosmic history. Some galaxies appear youthful and energetic, others seem mature and settled. A few look as though they've endured spectacular accidents and are still recovering from the experience. If galaxies could talk, some would probably have very long stories to tell. Others might simply sigh and say, "It's been a complicated few billion years." Another surprising aspect of galaxies is how much of them we cannot actually see. When most people picture a galaxy, they imagine stars, bright points of light scattered through space. That's understandable. Stars are the visible part. But modern astronomy suggests that galaxies contain far more than meets the eye. Surrounding every major galaxy is a vast halo of something known as dark matter. Dark matter remains one of science's greatest mysteries. We can't see it directly, we can't touch it, it doesn't emit light. Yet its gravitational influence appears everywhere. Without dark matter, galaxies as we know them might not exist at all. It's as though every galaxy carries an invisible framework supporting its structure, a hidden architecture stretching far beyond the stars we can observe. This realization added another layer of wonder to the study of galaxies. The visible universe suddenly became only part of the story. The more we learned, the more complex everything became. Fortunately, complexity doesn't have to be intimidating. In fact, tonight we'll approach these galaxies the same way one might explore an unfamiliar city. Slowly, patiently, without rushing. We'll look at their shapes, their histories, their unusual features, the events that built them, and the forces that continue shaping them today. By the end of our journey, you'll have travelled from the familiar structure of our own Milky Way to some of the strangest galaxies ever discovered. You'll meet giant spirals, quiet ellipticals, tiny dwarfs, galaxies forming stars at incredible rates, galaxies feeding enormous black holes, galaxies colliding with one another in slow-motion encounters that last hundreds of millions of years. And perhaps most importantly, you'll begin to see that galaxies are not isolated objects scattered randomly through space. They are connected. Each one is part of a larger story. A story that stretches across the observable universe itself. A curious thing happens when we look up at the night sky. At first, it appears scattered. Stars seem sprinkled across the darkness almost randomly, like grains of sand tossed onto black velvet. Some shine brightly. Others are faint and easy to miss. A few form familiar patterns that humans have been connecting into constellations for thousands of years. But the longer astronomers studied the universe, the more they realized that randomness is not really the story. The universe has structure. Stars gather together. Planets gather around stars. Moons gather around planets. And on scales so vast they challenge the imagination, entire populations of stars gather into galaxies. That raises an interesting question. Why? Why do galaxies exist at all? Why didn't the universe simply create stars evenly distributed throughout space? Why are there these enormous islands containing billions or even trillions of stars instead of a smooth cosmic fog stretching endlessly in every direction? To answer that question, we need to travel back to a time before the first galaxy existed. Back before the Milky Way. Back before Earth. Back before the Sun. Back before there were any stars at all. The story begins roughly 13.8 billion years ago with the event we call the Big Bang. Now, despite the name, the Big Bang was not an explosion in space. It was the rapid expansion of space itself. That's an important distinction. When many people hear the word explosion, they imagine something detonating from a central point and expanding outward into an empty surrounding area. The universe did something stranger. Space itself expanded everywhere at once. There was no center, no edge, no empty room waiting outside. The universe wasn't expanding into anything. The universe was creating the very stage upon which everything else would eventually appear. For the first moments after the Big Bang, conditions were unimaginably extreme. Temperatures were so high that atoms could not exist. Matter and energy existed in a dense, turbulent state that would look utterly alien to us. If you somehow found yourself there, which fortunately is impossible, you wouldn't see stars or planets or galaxies. You wouldn't see anything recognizable at all. The universe was far too hot and crowded. As expansion continued, however, something important happened. Space grew larger, and as space expanded, temperatures dropped. This cooling allowed particles to begin combining into more stable forms. First came protons and neutrons. Later came the first atomic nuclei. Eventually, hundreds of thousands of years after the Big Bang, electrons joined those nuclei, creating the first complete atoms. Most of these atoms were hydrogen, a smaller amount was helium, and tiny traces of a few other elements existed as well. That's it, no carbon, no oxygen, no iron, no gold, no calcium for bones, no silicon for computers. The universe at this stage was remarkably simple. Just enormous clouds of hydrogen and helium spread throughout expanding space. For a while, the universe entered what astronomers sometimes call the cosmic dark ages. It's a dramatic name, but an appropriate one. There were no stars yet. No galaxies, no sources of visible light. The universe was filled with matter, but it remained dark. Imagine an ocean stretching beyond every horizon. Calm, quiet, featureless. Now imagine waiting millions of years, then millions more. Gradually, tiny differences in density began changing everything. This part of the story is surprisingly important. The early universe was extremely uniform. Not perfectly uniform, but remarkably close. If matter had been distributed completely evenly, galaxies might never have formed. There would have been nothing to trigger the process. Fortunately for us, the universe contained tiny irregularities. Some regions possessed slightly more matter than others. Not much more, just enough. A region might contain one part in 100,000 more matter than a neighbouring region. At first glance, that difference sounds insignificant. Yet gravity is patient. Gravity doesn't need dramatic advantages, it simply keeps pulling and pulling and pulling. A slightly denser region possesses slightly stronger gravity. That stronger gravity attracts additional matter. As more matter arrives, gravity grows stronger still, which attracts even more matter. The process feeds itself. Tiny differences become larger differences. Small clumps become larger clumps. Over immense spans of time, structure begins emerging. It's a little like snow accumulating on a hillside. A small bump gathers slightly more snow than the surrounding area. That extra snow creates a larger bump. The larger bump gathers even more snow. Eventually a noticeable drift forms where almost nothing existed before. Gravity was doing something similar on cosmic scales. Slowly, steadily, relentlessly. Yet ordinary matter alone wasn't the whole story. Dark matter appears to have played an enormous role as well. Although we still don't fully understand what dark matter is, astronomers believe it provided the scaffolding upon which galaxies were built. Long before stars formed, vast halos of dark matter had already begun assembling. These invisible structures created gravitational wells. Ordinary matter fell into those wells. Hydrogen gathered, helium gathered, clouds became denser. The universe was laying foundations before constructing buildings. It's rather remarkable to think about. The largest structures we see today may have begun with tiny fluctuations present shortly after the birth of the universe itself. The seeds were planted very early. The harvest simply took billions of years to arrive. As matter continued accumulating, conditions eventually reached a critical point. Some regions became dense enough for gravity to overwhelm expansion locally. Clouds began collapsing inward. As they collapsed, pressure increased, temperatures rose, atoms collided more frequently. The centers of these growing clouds became hotter and hotter. Then something extraordinary happened. Nuclear fusion ignited, the first stars were born. No human witnessed those first stars. No planet existed to host observers. No eyes were present anywhere in the universe, yet their arrival transformed everything. After hundreds of millions of years of darkness, light returned. The cosmos switched on. These earlier stars were probably very different from many stars we see today. Astronomers believe they were enormous. Some may have contained hundreds of times the mass of the Sun. They burned brilliantly, they lived briefly, and they died dramatically. Massive stars consume their fuel quickly. The bigger the star, the shorter its lifespan tends to be. Some of those first stars may have survived only a few million years. That sounds like a long time from a human perspective. For a star, it is surprisingly brief. When they died, many exploded as supernovae. Those explosions scattered newly created elements throughout space. For the first time, carbon, oxygen, nitrogen, and many other elements entered the universe in significant quantities. The cosmos was becoming chemically richer. Future generations of stars would inherit those materials. Eventually planets would inherit them too. And billions of years later, living creatures would emerge from atoms forged inside long-dead stars. That connection never stops being astonishing. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of it traces back to stars. The universe had begun with mostly hydrogen. Stars changed that forever. Meanwhile, the regions where stars formed continued growing larger and more complex. Individual stars rarely formed alone. Entire populations emerged together. Clusters developed. Massive concentrations of matter accumulated. Gravity continued organizing everything into increasingly large structures. Gradually, the first galaxies appeared. These early galaxies probably looked quite different from many modern galaxies. The universe was younger. Conditions were rougher. Collisions occurred more frequently. Gas supplies were abundant. Star formation rates were often intense. Instead of the elegant spirals commonly shown in astronomy books, many early galaxies may have appeared chaotic and irregular. Imagine a rapidly growing city. Construction cranes everywhere. Roads unfinished. Buildings rising in every direction. Traffic moving unpredictably. Compare that to a mature city centuries later, where neighborhoods have settled into recognizable patterns. Early galaxies were more like the first scenario, busy, messy, energetic, still figuring themselves out. As billions of years passed, galaxies continued evolving. Some merged with neighboring galaxies, others consumed smaller companions. Many underwent repeated cycles of star formation. Each event altered their appearance. Each interaction reshaped their future. One of the most important lessons astronomers have learned is that galaxies are not permanent objects frozen in time. They're dynamic systems, living histories written in stars and gas. A galaxy observed today represents a single moment in a very long story. Consider our own Milky Way. It did not emerge fully formed. Instead, it grew gradually through countless interactions and mergers. Even now it continues evolving. Several dwarf galaxies orbit around it. Some are slowly being pulled apart by gravity. Their stars are being absorbed into the Milky Way itself. In a sense, our galaxy is still under construction, and it always has been. The same is true across the universe. Galaxies grow, change, collide, transform. Nothing remains completely unchanged. That's one reason astronomers find them so fascinating. Each galaxy acts like a historical archive. Its structure contains clues about everything it has experienced. Its stars reveal information about its age. Its chemical composition reveals details about previous generations of stars. Its shape reveals evidence of ancient interactions. Learning to read a galaxy is a bit like learning to read a biography. The details matter. Every feature tells part of the story. Another surprising fact is that galaxies solved a problem the universe faced very early on. Stars alone cannot easily remain organised forever. Over immense timescales, gravitational interactions would gradually scatter many stars. Galaxies provide the framework that keeps enormous stellar populations together. Dark matter halos help hold galaxies in place. Gravity maintains structure. Stars remain bound to larger systems. Without galaxies, the universe would likely look dramatically different. The environments necessary for long-term star formation might be far less common. Planetary systems could be rarer. The conditions that eventually allowed life to emerge might never have developed in the same way. It's impossible to know for certain, but galaxies appear to be among the universe's most important organising structures. They're not merely collections of stars, they're ecosystems, cosmic environments where stars are born, evolve, and die. Places where chemical complexity increases over time. Places where planetary systems emerge. Places where black holes grow. Places where matter is continually recycled from one generation to the next. And perhaps most remarkably, they're places where observers can eventually appear and ask questions about their origins. There's a certain symmetry in that. The universe spent billions of years building galaxies. Inside one of those galaxies, around one ordinary star, intelligent life emerged, and that life eventually developed telescopes capable of looking back across cosmic history. The galaxies created the conditions that allowed someone to wonder why galaxies exist. Not a bad achievement for a collection of stars and gas. Of course, the story doesn't stop with the first galaxies. Once galaxies existed, diversity followed. Different environments produced different outcomes. Some galaxies remained relatively small. Others grew into giants. Some developed elegant spiral structures. Others became smooth elliptical systems. A few evolved into forms so unusual that astronomers still debate exactly how they formed. The variety is extraordinary, yet all of those different galaxies trace their origins back to the same basic ingredients: gravity, hydrogen, time, and tiny fluctuations present near the beginning of the universe. It's a reminder that complexity often emerges from simple rules repeated over enormous timescales. The first galaxies were not the final destination. They were the beginning of a much larger story. A story that eventually produced the magnificent structures we observe today. When most people picture a galaxy, they're usually imagining a spiral galaxy. Even if they've never studied astronomy, even if they couldn't name a single galaxy beyond the Milky Way. Somehow the image feels familiar. A bright central glow surrounded by graceful arms winding outward through space. It's a shape that appears in science books, documentaries, observatory posters, and computer screensavers. If galaxies had celebrities, spiral galaxies would be the ones constantly appearing on magazine covers, and honestly, it's easy to understand why. They're beautiful. Not beautiful in a dramatic or exaggerated sense. Beautiful in the way a snowflake is beautiful, or a seashell, or a whirlpool in a river. Their structure feels both orderly and natural at the same time. Yet beneath that elegance lies something astonishing. A spiral galaxy is not a solid object spinning like a pinwheel toy. It only looks that way. The reality is far stranger. Let's begin with our own home, the Milky Way. For thousands of years, humans had no idea they lived inside a galaxy. People looked upward and saw stars scattered across the sky. They saw the pale band of light stretching overhead on dark nights, but nobody knew exactly what it was. Ancient cultures created stories about it. Some imagined it as a celestial river. Others saw a pathway used by spirits. Many civilizations treated it as something sacred. Those interpretations may have differed, but they shared one thing in common. Nobody realized they were looking at the inside of an enormous spiral galaxy. It's a bit like being born inside a vast forest and spending your entire life among the trees without ever realizing you're surrounded by one of the largest ecosystems on Earth. Perspective changes everything. The Milky Way contains somewhere between 100 billion and 400 billion stars. Even that estimate remains uncertain. Astronomers are still refining the numbers. After all, counting stars across a structure 100,000 light-years wide is not exactly a simple afternoon project. Our Sun occupies a position roughly halfway between the galaxy's centre and its outer edge. We're not in a privileged location. We're not near the middle. We're not particularly close to the edge. We're simply residents of an ordinary neighbourhood within a very large cosmic city. That fact alone is worth pausing to appreciate. Every human who has ever lived, every civilization, every historical event, every invention, every dream, every argument over parking spaces, all of it has taken place within a tiny corner of one spiral galaxy, and there are countless others. So what exactly creates the spiral shape? At first glance, the answer seems obvious. The galaxy rotates. The rotation twists everything into spirals. Simple. Unfortunately, nature rarely allows things to remain that simple. Imagine painting a few bright lines across a spinning pizza dough. As the dough rotates, those lines would quickly wind tighter and tighter until they became an indistinguishable mess. Astronomers call this the winding problem. If spiral arms were made of fixed groups of stars rotating together, they should eventually wrap themselves into impossibly tight structures. Yet when we observe spiral galaxies throughout the universe, we consistently find well-defined spiral arms. Something else must be happening. The solution emerged through a concept known as density wave theory. Rather than being permanent collections of stars, spiral arms are better understood as traffic jams, cosmic traffic jams. Now that's not a phrase you hear every day. Picture a busy highway. Cars enter and leave a traffic jam continuously. The individual vehicles move through the congestion, yet the traffic jam itself can persist. The location remains recognizable, even though the cars within it constantly change. Spiral arms work in a somewhat similar way. Stars, gas clouds, and dust move through the arms over time. The arm itself represents a region where material becomes temporarily concentrated. Gravity gently organizes matter into these patterns. As gas enters these dense regions, something important happens. Star formation accelerates. Massive clouds of hydrogen begin collapsing under their own gravity. New stars ignite. Some of them become enormous, many times larger than our Sun, extremely hot, extremely bright, and intensely blue. These young stars illuminate the spiral arms, making them stand out across intergalactic distances. When we admire photographs of spiral galaxies, we're often looking at regions filled with relatively young stars. The bright arms are cosmic neighbourhoods where stellar birth is actively taking place. Meanwhile, older stars continue orbiting quietly throughout the galaxy. In a sense, spiral arms are among the universe's busiest construction zones. New stars are constantly appearing. Old stars continue their journeys. Gas clouds drift through. Gravity keeps everything moving. The result is a structure that appears stable, even though countless changes are occurring every second. This process has been unfolding for billions of years. Another feature found in spiral galaxies is the central bulge. Near the middle of most spirals sits a dense concentration of older stars. Viewed from a distance, it often appears as a bright glowing core. The stars here tend to be older than those found within the spiral arms. Many formed long ago during earlier stages of galactic evolution. Because they're generally older and cooler, these stars often appear more yellow or reddish, compared to the bright blue stars forming in the arms. The contrast creates one of the most recognizable appearances in astronomy. A golden central region surrounded by sweeping blue-white arms. It's almost as if the galaxy carries its history visibly. The older generations occupy the center. The younger generations flourish farther out. Of course, the center contains something even more remarkable. At the heart of the Milky Way lies a supermassive black hole known as Sagittarius, a star. Its mass equals roughly 4 million suns. That sounds enormous because it is. Yet compared with black holes found in some other galaxies, it's actually fairly modest. Astronomers now believe that most large galaxies contain supermassive black holes at their centres. The relationship between galaxies and these black holes remains one of modern astronomy's most fascinating puzzles. Did the galaxies help grow the black holes? Did the black holes help shape the galaxies? Did both evolve together? The answer appears complicated, which is science's polite way of saying, we're still working on it. Moving outward from the centre, spiral galaxies reveal another surprise. They're not flat. Photographs often make them appear like cosmic pancakes. In reality, they possess thickness. Stars move above and below the galactic plane. Gas and dust form layers. The structure resembles a disk rather than a sheet of paper. If you could somehow view the Milky Way from the side, it would look more like a flying saucer than a pinwheel. That perspective changes dramatically depending on where you observe it. Some spiral galaxies face us directly, displaying their magnificent arms in full detail. Others appear edge-on. In those cases, we see a thin glowing line crossed by dark bands of dust. One particularly famous example is the Sombrero Galaxy, whose appearance resembles the broad-brimmed hat that inspired its nickname. Astronomy often becomes easier when objects conveniently resemble everyday things. Not always scientifically rigorous, perhaps, but undeniably helpful. Spiral galaxies also vary enormously in size. Some contain only a few billion stars, others host hundreds of billions. A few become truly gigantic. One example is the Andromeda Galaxy, the nearest large spiral galaxy to our own. Located about 2.5 million light-years away, Andromeda contains roughly 1 trillion stars. That's several times the stellar population of the Milky Way. If galaxies were cities, Andromeda would qualify as a sprawling megacity. Interestingly, Andromeda and the Milky Way are moving toward each other. Not quickly by everyday standards, quickly by galactic standards. Their collision is expected to occur roughly 4 to 5 billion years from now. That might sound alarming. Fortunately, galaxies are mostly empty space. Stars rarely collide directly. Instead, the overall structures gradually merge. The shapes become distorted. Gravity rearranges orbits. New bursts of star formation occur. Eventually, a completely new galaxy emerges. Future inhabitants of Earth, assuming Earth still exists and someone is around to watch, would witness an extraordinary transformation of the night sky. Of course, predicting parking availability after a galactic merger remains somewhat beyond current science. Not all spiral galaxies look identical. Some possess tightly wound arms. Others display loose sweeping structures. Certain spirals contain 2 major arms. Others contain several. Some appear symmetrical. Others seem slightly lopsided. These differences arise from variations in mass, rotation, interactions with neighbouring galaxies, and internal dynamics. Nature rarely mass-produces perfect copies. Every galaxy develops its own character. One particularly fascinating aspect of spiral galaxies involves colour. Astronomers learn a tremendous amount by studying galactic colours. Blue regions usually indicate young stars. Redder regions often suggest older populations. Dust appears dark. Gas glows under specific conditions. A single image can reveal clues about millions or billions of years of history. It's a bit like examining tree rings, except the tree is 100,000 light-years wide. Spiral galaxies are also rich in raw materials. Hydrogen gas remains abundant throughout their disks. That gas acts as fuel for future generations of stars. As long as enough gas remains available, star formation continues. Slowly, steadily, sometimes dramatically. This ongoing creation helps explain why spiral galaxies often appear vibrant and active. They're still building, still evolving, still producing new stars. In contrast, some other galaxy types have already exhausted much of their available gas. We'll encounter those later. For now, it's enough to appreciate that spiral galaxies remain among the universe's most productive stellar factories. Astronomers have discovered spiral galaxies throughout the observable universe. Some exist relatively nearby, others appear at tremendous distances. Because light requires time to travel, observing distant galaxies allows us to look backward into history. A galaxy located 1 billion light-years away appears as it existed 1 billion years ago. More distant galaxies reveal even earlier stages of cosmic evolution. In effect, telescopes become time machines. Every observation captures a different moment in the universe's past. This has allowed scientists to investigate how spiral galaxies evolved over billions of years. Evidence suggests that many galaxies began as smaller structures. Repeated mergers and growth gradually produced the magnificent spirals we observe today. Their formation wasn't instantaneous. It required immense periods of time, gravity patiently assembling matter, star formation reshaping environments, collisions altering trajectories. The process continues even now. Nothing about a galaxy is truly finished. That's one of the most remarkable things about astronomy. The universe is not a museum filled with static exhibits. It's active, dynamic, constantly changing. The spiral galaxy you admire today differs from the galaxy that existed 100 million years ago, and it will differ again 100 million years from now. Those changes simply occur on timescales much longer than human lives. Even so, traces of these transformations remain visible. Astronomers regularly find evidence of smaller galaxies being absorbed by larger spirals. Streams of stars stretch through space like faint fingerprints left behind by ancient encounters. The Milky Way itself is currently consuming several dwarf galaxies. Not in a violent science fiction sense, more in the slow, gravitational sense, which admittedly sounds less dramatic but is no less fascinating. Gravity is patient. Given enough time, it can accomplish astonishing things. Looking at a spiral galaxy through a telescope can feel strangely calming. Perhaps it's the symmetry, perhaps it's the scale. Perhaps it's the realization that structures containing hundreds of billions of stars can still organize themselves into patterns that seem almost familiar. Whirlpools, shells, storm systems, spirals appear throughout nature. From tiny organisms to giant galaxies, the universe seems remarkably fond of them. Take a look at enough spiral galaxies and sooner or later you'll begin noticing something curious. Many of them don't actually look quite the way people expect. The classic image of a spiral galaxy usually shows graceful arms emerging directly from a bright circular center. It's neat, symmetrical, exactly the sort of thing that ends up on posters and textbook covers. Then astronomers started observing galaxies in greater detail, and suddenly a large number of spirals seemed to be hiding an extra feature right in the middle. Instead of a simple round core, they possessed a long bright structure stretching across the center, a kind of stellar beam, a luminous bridge. A straight line of stars cutting through the galaxy's heart before the spiral arms curved outward from either end. This structure became known as a bar, and galaxies that possess one are called barred spiral galaxies. At first glance, the distinction may seem minor. A spiral galaxy with a bar, a spiral galaxy without one. Perhaps not the most dramatic difference in the universe. But as astronomers continued studying these systems, they discovered something remarkable. That bar isn't merely decoration. It's one of the most important structures a galaxy can develop. In some ways, it functions like a giant transportation network, a stellar highway stretching across tens of thousands of light years, a mechanism capable of moving enormous quantities of gas and stars through the galaxy. And as it turns out, our own Milky Way belongs to this category. For a long time, astronomers weren't completely certain. Being inside the Milky Way makes it difficult to photograph from the outside for obvious reasons. Imagine trying to determine the shape of an entire forest while standing among the trees. You can study nearby trunks, you can estimate directions, you can collect clues. But seeing the complete structure remains challenging. For decades, researchers debated whether the Milky Way possessed a central bar. Eventually, improved infrared observations provided the answer. Yes, our galaxy contains a substantial bar crossing its central region. The discovery helped explain many features of the Milky Way's structure and behaviour, which means that right now, every human being resides inside a barred spiral galaxy. We're all living in a cosmic city with a stellar highway running through downtown. Not a bad address, really. The question, of course, is why these bars form in the first place. Galaxies don't wake up one morning and decide they need better infrastructure. At least as far as current evidence suggests. Instead, bars emerge naturally from gravity and motion. To understand how, imagine a rotating disk made of billions of stars. Each star follows its own orbit around the galactic centre. The entire system appears stable, yet beneath that apparent stability, countless gravitational interactions are taking place. Stars influence one another, gas clouds shift, small imbalances develop. Over long periods, those imbalances can grow. Eventually, the central region becomes elongated rather than perfectly circular. The galaxy begins developing a bar. This process unfolds incredibly slowly. Millions of years pass, then tens of millions, then hundreds of millions. The structure gradually strengthens. From a human perspective, it would appear completely motionless. From a galactic perspective, it's an ongoing transformation. What's especially fascinating is that barred spirals are not rare exceptions. In fact, they may be the dominant form of spiral galaxy in the universe. Observations suggest that roughly 2/3 of all spiral galaxies contain bars. Some bars are short and subtle, others stretch across enormous distances. Many of the most impressive galaxies ever photographed belong to this category. One famous example is the NGC 1300. Located roughly 60 million light-years away, it displays one of the clearest barred structures ever observed. Viewed from Earth, it almost appears designed by an artist. A brilliant central bar extends across the core. Elegant spiral arms emerge from each end. The entire galaxy seems carefully arranged, yet every detail arose through natural processes. Gravity doing what gravity does best, organising matter over immense stretches of time. Another famous barred spiral is the NGC 1365. Sometimes nicknamed the Great Barred Spiral Galaxy, it spans more than 200,000 light-years. That's roughly twice the diameter of the Milky Way. Its central bar is enormous. Its spiral arms stretch outward like vast celestial rivers, and hidden within its core lies a supermassive black hole containing millions of times the mass of our Sun. Astronomers often use galaxies like these to understand how bars influence galactic evolution. Because the influence turns out to be substantial, let's return to the idea of a stellar highway. Imagine a city with roads connecting distant neighbourhoods to the downtown area. Those roads allow traffic to flow inward and outward. Resources move efficiently. Activity concentrates in important regions. Something similar happens inside barred spiral galaxies. The bar helps funnel gas toward the galactic centre. Not all at once, not dramatically, but steadily. Gas clouds gradually migrate inward along the bar's structure. Over time, enormous amounts of material accumulate near the centre, and when gas gathers in sufficient quantities, interesting things happen. Stars begin forming, sometimes in extraordinary numbers. Astronomers have observed many barred galaxies experiencing intense bursts of star formation near their cores. It's almost as though the bar acts like a conveyor belt, delivering raw materials to a giant construction site. The result can be a bustling central region packed with newly formed stars. This process may also influence the supermassive black hole at the galaxy's centre. Black holes require fuel. They grow by consuming matter. The inward movement of gas provided by the bar may help feed these central monsters. In some galaxies, this can trigger tremendous activity. Material spiralling toward the black hole becomes extremely hot. Radiation pours outward. The galactic nucleus brightens dramatically. We'll explore those active galaxies in greater detail later in our journey. For now, it's enough to appreciate that the bar may serve as an important supply route, a structure capable of delivering material directly to the central engine. Of course, bars don't only affect gas, they influence stars as well. The gravitational forces associated with the bar alter stellar orbits throughout the galaxy. Rather than moving in simple circular paths, many stars follow more complicated trajectories. Some become trapped within the bar itself. Others respond to the changing gravitational environment in subtle ways. The entire galaxy becomes a dynamic system shaped by these interactions. One reason astronomers find barred spirals so fascinating is that they reveal galaxies in motion. Not motion we can watch directly. The timescales remain far too long. But motion inferred through observation and mathematics. The bar provides evidence that galaxies are evolving structures rather than static collections of stars. And evolution raises another interesting question. Do bars last forever? The answer appears to be no, at least not necessarily. Current research suggests that bars may strengthen, weaken, and sometimes disappear over a galaxy's lifetime. A galaxy that possesses a prominent bar today may not have possessed one billions of years ago. Likewise, some galaxies currently lacking bars may develop them in the future. The universe is not merely classifying galaxies into fixed categories, it is transforming them continuously. That's an important idea to remember throughout our exploration. Astronomical categories help us understand patterns. They do not represent permanent identities. Galaxies evolve, they grow, they interact, they change. A barred spiral is not simply a thing, it's a stage within a much longer story. Interestingly, observations of the distant universe suggest that bars were less common in earlier cosmic history. When astronomers examine galaxies billions of light years away, they're seeing them as they existed billions of years ago. Those ancient galaxies often appear more chaotic, less organized, more turbulent. Bars become increasingly common later. This suggests that bars may emerge as galaxies mature and settle into more stable structures. It's a bit like watching cities develop over time. Young settlements may appear irregular and disorganized. As they grow, transportation networks emerge. Roads become established. Infrastructure develops. The comparison isn't perfect, but the underlying idea is surprisingly similar. Organization arises gradually. Some barred spirals exhibit especially striking features called rings. Gas flowing through the galaxy can accumulate in specific regions, creating circular structures surrounding the bar or the core. These rings often become sites of intense star formation. The result can be spectacular. A galaxy may display a central bar surrounding rings and sweeping spiral arms all at once. The architecture becomes increasingly elaborate, yet gravity remains the master designer behind it all. One particularly beautiful example is the NGC 1097. This galaxy contains a prominent bar and remarkable ring structures near its center. Photographs reveal clusters of young stars forming in these regions, creating a dazzling display of cosmic activity. Looking at images like these, it's easy to forget the immense scales involved. Those bright patches may span thousands of light years. Individual star-forming regions can dwarf entire stellar neighborhoods. Everything appears compact in photographs. Reality is much larger. Astronomy frequently teaches that lesson. The universe is almost always bigger than it first appears. Bars may also influence the future shape of spiral galaxies. By redistributing gas and stars, they gradually alter the galaxy's overall structure. Some researchers believe that bars contribute to the growth of central bulges. Over long periods, material transported inward accumulates near the core. The central region becomes more massive. The galaxy slowly changes its appearance. Again, these processes occur over billions of years. No single generation could witness them directly. Yet their cumulative effects become obvious when astronomers compare large populations of galaxies. Patterns emerge, relationships become visible. The story begins to make sense. One aspect of barred spirals that often surprises people is how orderly they appear despite being composed of billions of independently moving stars. Imagine attempting to coordinate the movement of hundreds of billions of objects across distances measured in thousands of light years. The task seems impossible, and yet nature accomplishes it without central planning. No galactic traffic controller sits in the core issuing instructions. No cosmic engineer oversees the process. Gravity alone creates the patterns, simple physical laws operating consistently across vast scales. There's something quietly impressive about that. The same force that causes an apple to fall toward Earth helps organize entire galaxies. Scale changes, principles remain. As our understanding of barred spirals has improved, astronomers have come to view them not as unusual variants, but as key players in galactic evolution. Their bars transport material, influence star formation, feed central black holes, reshape internal structures, and perhaps most importantly reveal that galaxies are constantly evolving. They're not frozen snapshots, they're active systems, living histories written across billions of years. The Milky Way itself continues following this path. Its bar continues exerting influence. Stars continue orbiting. Gas continues flowing. New stars continue forming. After spending time among spiral galaxies, it's easy to assume that most galaxies should look roughly similar. A bright centre, graceful arms, ongoing star formation. Perhaps a central bar guiding material inward. The general picture feels familiar. Then astronomers point their telescopes toward a completely different class of galaxies, and suddenly the universe seems to change its mind. The first thing you notice is what's missing. No spiral arms, no obvious disk, no sweeping structure winding outward from the centre. Instead, these galaxies appear smooth, rounded, sometimes nearly circular, sometimes stretched into long oval shapes. At first glance, they can seem almost simple compared to the dramatic appearance of spirals, but appearances can be deceptive, because hidden behind that smooth exterior are some of the largest, oldest, and most massive galaxies in the entire universe. These are elliptical galaxies, and while spiral galaxies often feel energetic and busy, elliptical galaxies possess a very different personality. If a spiral galaxy resembles a thriving city full of construction projects, traffic, and new neighbourhoods appearing all the time, an elliptical galaxy feels more like an ancient capital that has already seen most of its major growth. The lights are still on, the residents are still there, but the frantic building phase largely ended long ago. That comparison isn't perfect, of course. Galaxies don't have personalities, at least not officially. Yet astronomers often find themselves describing ellipticals in surprisingly similar terms. They're quiet, they're mature, they're stable, and in many cases they're absolutely enormous. To understand elliptical galaxies, it's worth starting with their appearance. Unlike spirals, which display clear internal structures, ellipticals often look like giant glowing clouds. The light gradually fades from the centre toward the outer regions. There's no obvious pattern, no distinct arms, no dramatic dust lanes. Just billions or even trillions of stars blended together into a smooth, luminous shape. Astronomers classify ellipticals according to how stretched they appear. Some are nearly spherical, others are noticeably elongated. The classification system ranges from E0 to E7. An E0 galaxy appears almost perfectly round. An E7 galaxy looks much more elongated. Interestingly, the classification tells us nothing about size, only shape. An enormous elliptical galaxy and a much smaller one might receive similar designations if they have comparable proportions. One reason elliptical galaxies appear so different from spirals involves the motions of their stars. In a spiral galaxy, stars generally orbit within a rotating disk. That organised motion helps create the familiar structure. Elliptical galaxies are different. Their stars move in many directions. Some travel one way, others move another. The overall motion resembles a giant swarm rather than a neatly rotating disk. Imagine the difference between cars travelling along organised highways and bees moving throughout a large hive. Both involve motion. One is highly structured, the other is far more random. That randomness helps explain the smooth appearance of elliptical galaxies. Without a dominant rotating disk, spiral arms fail to develop. Instead, the galaxy settles into a more rounded shape. Of course, appearance is only part of the story. What truly distinguishes elliptical galaxies is their stellar population. Remember how spiral arms often glow blue because they're filled with young stars? Ellipticals generally lack those bright blue regions. Most of their stars are old, very old. Many formed billions of years ago during intense periods of star formation early in the galaxy's history. Since then, relatively few new stars have appeared. As a result, elliptical galaxies often display a yellowish or reddish colour. The youthful blue stars are largely absent. The older stars dominate the light. It's almost as if the galaxy has entered a quieter phase of life. The factories that once produced vast numbers of new stars have mostly shut down. The reason comes down to fuel. Stars require gas to form, specifically enormous clouds of hydrogen and other materials. Spiral galaxies usually contain plenty of this raw material. Elliptical galaxies often do not. At some point in their history, much of the available gas was consumed, expelled, or heated to temperatures that made star formation difficult. Without sufficient cold gas, stellar birth rates decline dramatically. The galaxy becomes quieter, not dead, not inactive, simply less productive when it comes to creating new stars. This raises an important question. How do elliptical galaxies become this way? For many years, astronomers debated the answer. Today, evidence strongly suggests that galaxy mergers play a major role. Let's imagine two large spiral galaxies approaching one another. The process unfolds slowly. Hundreds of millions of years pass, then billions. Gravity begins distorting both systems. Spiral arms stretch, gas clouds collide, star formation erupts, the structures become increasingly chaotic. Eventually the galaxies merge completely. The result often bears little resemblance to either original galaxy. The organized disks disappear. The stellar motions become scrambled. The final product can be an elliptical galaxy. In essence, many ellipticals may be the descendants of ancient galactic collisions. They're what remains after some of the largest mergers in cosmic history. This idea is supported by computer simulations. When astronomers model galaxy collisions, the resulting structures frequently resemble real elliptical galaxies observed across the universe. It's one of the clearest examples of modern astronomy successfully connecting theory and observation. And nowhere is this easier to appreciate than when examining some of the most famous elliptical galaxies ever discovered. One excellent example is Messier 87, often abbreviated as M87. This galaxy resides within the Virgo cluster and ranks among the most studied galaxies in astronomy. M87 is truly enormous. It contains trillions of stars, not billions, trillions. Its diameter stretches across hundreds of thousands of light years. At its centre lies one of the most famous black holes ever observed. In fact, the first direct image of a black hole was obtained from the supermassive black hole inside M87 by the Event Horizon Telescope collaboration. That black hole contains billions of times the mass of the Sun. The image became one of the most iconic scientific achievements of the 21st century. What's particularly striking about M87 is its scale. The Milky Way is large. M87 is larger, much larger. If our galaxy feels like a major metropolis, M87 resembles an entire continent. Yet despite its immense size, it maintains the smooth, rounded appearance characteristic of elliptical galaxies. Another famous example is Messier 49, also known as M49. This galaxy holds a special place in astronomical history because it was the first member of the Virgo cluster ever discovered. Like many giant ellipticals, M49 contains a huge population of globular clusters. These are dense spherical collections of stars orbiting the galaxy. The Milky Way hosts around 150 known globular clusters. M49 possesses thousands. Imagine looking into the night sky and finding not hundreds of star clusters, but thousands orbiting a single galaxy. The scale becomes difficult to comprehend. Then there is Messier 60, another massive elliptical residing within the same cluster. M60 contains a supermassive black hole estimated to be several billion times more massive than the Sun. Observations suggest that this galaxy has undergone a long and complex evolutionary history involving multiple mergers and interactions. Today, it stands as another example of how giant elliptical galaxies often dominate the environments around them. Notice a pattern emerging here. Many of the largest elliptical galaxies reside inside galaxy clusters. This isn't a coincidence. Clusters create ideal conditions for mergers. Galaxies frequently interact. Collisions become more likely. Over billions of years, repeated mergers can produce enormous elliptical systems. In fact, some of the largest galaxies in the universe are known as CD galaxies. These are gigantic ellipticals occupying the centres of major galaxy clusters. One remarkable example is IC1101. For many years, IC1101 was considered one of the largest known galaxies in existence. Its diameter may exceed several million light-years depending on how its outer regions are measured. To appreciate that scale, remember that the Milky Way spans roughly 100,000 light-years. IC1101 operates on an entirely different level. It's difficult to even call it a galaxy without immediately needing several qualifiers. It feels more like a small universe unto itself. Despite their quiet appearance, elliptical galaxies are not entirely inactive. Many contain hot gas emitting powerful X-rays. Others host active supermassive black holes. Some continue absorbing smaller neighbouring galaxies. The difference is that these activities are often less visually obvious than the bright spiral arms and star-forming regions found in spirals. The drama still exists, it's simply occurring in different forms. One particularly fascinating feature of giant ellipticals involves dark matter. Evidence suggests that these galaxies are embedded within enormous dark matter halos. In many cases, the visible stars represent only a fraction of the galaxy's total mass. The majority remains invisible. Astronomers detect it indirectly through gravity. Stars orbit too quickly. Gas behaves unexpectedly. Galactic motions reveal hidden mass. The same mystery appears throughout the universe, but giant ellipticals often provide especially clear evidence. Another interesting difference involves dust. Spiral galaxies frequently contain extensive dust lanes. Ellipticals generally possess much less visible dust. That's one reason their appearance seems so smooth. There are fewer dark structures interrupting the light. The stars blend together into a continuous glow. Through a telescope, many ellipticals resemble giant golden lanterns floating in darkness. Simple at first glance, far more complicated upon closer inspection. As observations improved during the 20th and 21st centuries, astronomers began realizing that elliptical galaxies hold important clues about the early universe. Because their stars are often very old, studying those stars allows researchers to investigate conditions that existed billions of years ago. In some sense, giant ellipticals function as cosmic archives. Their stellar populations preserve records from ancient periods of galactic evolution. The stars themselves become historical documents. Every spectrum contains information. Every chemical signature tells part of a story. Every observation helps reconstruct events that occurred long before Earth even existed. And perhaps that's what makes elliptical galaxies so interesting. They don't immediately attract attention the way spirals do. There are no dramatic arms, no obvious pinwheel structure, no dazzling symmetry. Instead, they reveal their secrets gradually. The more carefully astronomers study them, the more impressive they become. Immense populations of ancient stars, supermassive black holes, histories shaped by colossal mergers, Structures spanning distances almost beyond imagination. They're quiet giants. Not because nothing happens inside them, but because most of the loudest events occurred long ago. By this point in our journey, we've encountered two galaxy families that seem very different from one another. Spiral galaxies are active, structured, and rich in gas. Their sweeping arms glow with young stars, and new stellar nurseries continue appearing throughout their disks. Elliptical galaxies, meanwhile, often appear calm and mature. Most of their stars formed long ago, and their supplies of star-forming gas have largely disappeared. Their smooth shapes hint at long histories shaped by mergers and gradual evolution. For a while, astronomers viewed these categories almost like separate worlds. Some galaxies were spirals, others were ellipticals. Simple enough. Then telescopes improved, observations accumulated, and researchers began noticing galaxies that didn't seem entirely comfortable in either category. These galaxies possessed disks like spirals, yet they lacked obvious spiral arms. They looked flattened rather than rounded. Yet they didn't contain the active star-forming regions commonly associated with spiral galaxies. It was as though nature had taken pieces from both families and combined them into something new. These objects became known as lenticular galaxies. Sometimes astronomers refer to them as S0 galaxies, and although they rarely receive the same attention as spirals or giant ellipticals, lenticular galaxies may hold some of the most important clues about how galaxies evolve over billions of years. In many ways, they are the universe's transitional forms, not quite one thing, not quite another, a kind of cosmic middle ground. The name itself comes from their appearance. Lenticular means lens-shaped. Viewed from certain angles, these galaxies resemble giant lenses floating through space. When seen face-on, they often appear as bright central bulges surrounded by smooth disks. Viewed edge-on, they can look remarkably similar to spirals. The difference becomes apparent when you search for spiral arms. They simply aren't there. Or if they once existed, they've become faint enough to disappear from view. This raises an obvious question. How can a galaxy have a disk but lack spiral arms? After all, spiral arms seem like one of the defining features of disk galaxies. The answer lies in the ingredients available to the galaxy. Remember what helps make spiral arms visible: young stars, gas clouds, ongoing star formation. Those brilliant blue stars illuminating the arms are relatively short-lived. Many survive only a few million years before exhausting their fuel. That's a brief lifespan by cosmic standards. If a galaxy stops producing new stars, those bright blue populations gradually disappear. The older stars remain. The underlying disk remains. But the dramatic appearance begins to fade. The result can look very much like a lenticular galaxy. In a sense, some lenticular galaxies may be spirals that have simply run out of fuel. The structure survives, the activity declines, the galaxy settles into a quieter state. Imagine a bustling city whose factories gradually shut down over many decades. The roads remain, the buildings remain, the neighborhoods remain. But the rapid growth slows. The atmosphere changes. The city still exists, but it feels different. Lenticular galaxies often create a similar impression. They retain evidence of their past while displaying signs of a quieter present. One reason astronomers find lenticular galaxies fascinating is that they may represent a bridge between spirals and ellipticals. Not necessarily in every case. Nature rarely follows a single rule. But many observations suggest that at least some lenticular galaxies formed when spiral galaxies lost the gas needed for star formation. Without fresh gas, the creation of new stars gradually stopped. The spiral arms faded. The galaxy evolved into something resembling an intermediate state. This possibility transforms lenticular galaxies into valuable laboratories. By studying them, astronomers can investigate what happens when galactic evolution slows down. They can observe a galaxy after much of its stellar production has ended, but before it becomes something entirely different. The universe does not provide many opportunities to watch long-term evolution directly. lenticular galaxies offer one of the best. To appreciate how important these objects are, let's look at some famous examples. One of the most well-known lenticular galaxies is NGC 5866. Many people know it by another name, the Spindle Galaxy. Located roughly 44 million light-years away, NGC 5866 appears spectacular when viewed edge-on. A bright central bulge dominates the middle. A thin disk stretches outward. Dark dust lanes cut across the structure. At first glance, some observers mistake it for a spiral galaxy seen from the side. Closer examination reveals something different. The obvious spiral structure is missing. Instead, the galaxy displays the smooth, orderly appearance typical of lenticular systems. The Spindle Galaxy demonstrates why classification can sometimes be challenging. Nature doesn't always provide clear boundaries. Sometimes galaxies occupy regions between categories. Another famous example is NGC 3115. Located in the constellation Sextans, NGC 3115 is one of the nearest large lenticular galaxies to Earth. Astronomers have studied it extensively because its relative proximity allows detailed observations. One particularly intriguing feature is the supermassive black hole residing at its centre. For many years, NGC 3115 contained one of the strongest cases for a central supermassive black hole before such objects became widely accepted. Today, we know that massive black holes are common in large galaxies. At the time, however, the evidence from NGC 3115 played an important role in changing scientific understanding. Then there's Messier 85, often abbreviated as M85. This galaxy resides in the Virgo cluster region and has puzzled astronomers for decades. Although classified as lenticular, M85 shows evidence of a surprisingly complex past. Observations suggest it may have experienced mergers and interactions that helped shape its present appearance. Like many lenticular galaxies, it refuses to fit neatly into a simple story. And perhaps that's one reason these galaxies remain so interesting. They challenge assumptions. They remind astronomers that evolution rarely follows a straight path. One important clue about lenticular galaxies comes from where they're found. A large number reside inside galaxy clusters. This is not a coincidence. Galaxy clusters are crowded environments. Hundreds or even thousands of galaxies occupy the same region of space. Interactions become common. Not necessarily direct collisions. Often the effects are more subtle. A galaxy moving through a cluster encounters enormous amounts of hot gas filling the space between galaxies. This gas may seem incredibly thin compared to Earth's atmosphere. Nevertheless, across galactic scales it can have significant consequences. As a spiral galaxy travels through this environment, pressure begins stripping gas from the galaxy. Astronomers call this process ram pressure stripping. The name sounds technical, but the basic idea is surprisingly intuitive. Imagine driving a car through heavy rain. Air resistance pushes against the vehicle. Now imagine a galaxy moving through an enormous cloud of hot gas. Over time, that gas can remove some of the galaxy's own gas. The process occurs slowly, but given hundreds of millions or billions of years, the effects become substantial. Without gas, star formation declines. Without new stars, spiral arms fade. The galaxy gradually begins resembling a lenticular system. This mechanism provides one possible route from spiral to lenticular. Another route involves galactic interactions. Even relatively gentle encounters can disturb gas distributions. Material may be removed. Star formation may surge briefly before exhausting available resources. The final result can again resemble a lenticular galaxy. What's fascinating is that multiple evolutionary pathways may lead to similar outcomes. Nature often works that way. Different histories can produce surprisingly similar appearances. Astronomers sometimes compare this situation to biology. Two animals might evolve similar traits through entirely different processes. Likewise, two lenticular galaxies might look alike while possessing very different pasts. That realization has encouraged researchers to study these galaxies in ever greater detail. Every clue matters. the ages of the stars, the chemical composition, the amount of remaining gas. The motions of stars within the disk. Each measurement helps reconstruct the galaxy's history. One particularly useful tool involves stellar populations. Remember how spiral galaxies often contain many young blue stars? Lenticular galaxies typically contain older populations, not as old as some giant ellipticals in every case, but generally older than active spirals. The colours reveal this difference. Instead of brilliant blue arms, lenticular galaxies often display warmer yellow and reddish tones. Those colours tell a story of declining star formation, a story of aging stellar populations, a story written across billions of years. Interestingly, not all lenticular galaxies are completely inactive. Some retain modest amounts of gas, others continue forming stars at low rates. Again, nature refuses to obey simple categories. Astronomers classify galaxies because classifications are useful. The galaxies themselves do not always cooperate. There are lenticular systems that appear almost spiral-like. Others look remarkably close to ellipticals. Many occupy positions somewhere in between. This ambiguity is precisely what makes them valuable. If galaxies evolved in perfectly distinct categories, understanding their histories would be easier, but probably less interesting. Lenticular galaxies remind us that evolution is gradual, changes accumulate, structures transform, boundaries blur. Another remarkable feature of many lenticular galaxies is the prominence of their central bulges. In numerous cases, the bulge appears larger relative to the disk than in typical spiral galaxies. This may provide clues about how they evolved. Processes that transport material toward the centre can increase the bulge's mass over time. Mergers may contribute, bars may contribute, environmental effects may contribute. The challenge lies in determining which processes dominated for any particular galaxy. Astronomers are essentially acting as cosmic detectives. The evidence is billions of years old. The witnesses are unavailable. The crime scene spans tens of thousands of light years. Yet somehow, piece by piece, the story emerges. Modern telescopes have revealed even more complexity. Some lenticular galaxies contain faint ring structures. Others possess subtle traces of old spiral patterns. A few show evidence of past mergers hidden within their stellar motions. At first glance, they may appear smooth and uncomplicated. Closer inspection often reveals a rich history. The situation is somewhat like examining an old building. From the outside, it seems straightforward. Then you begin exploring. You discover renovations, extensions, repairs, evidence of earlier designs hidden beneath newer layers. Galaxies preserve history in much the same way. One particularly exciting development has come from observations made by the James Webb Space Telescope. https://www.jwst.nea.gov $UTM_source = chatgpt.com and other advanced observatories. These instruments allow astronomers to study distant galaxies in unprecedented detail. As researchers look farther into the universe's past, they gain new insights into how galaxy populations evolved over time. The emerging picture suggests that lenticular galaxies play a significant role in that story. They're not rare curiosities, they're important participants in galactic evolution. And perhaps that's the most interesting thing about them. Spiral galaxies often attract attention because they're beautiful. Giant ellipticals attract attention because they're enormous. Lenticular galaxies quietly occupy the space between. For decades they were sometimes overlooked. Yet they may help explain how one galactic state transitions into another. They may preserve evidence of environmental effects, mergers, gas loss, and long-term evolution. In other words, they help connect the dots. And the more astronomers study them, the more those connections seem to matter. Because the universe isn't merely filled with categories, it's filled with transformations. Spirals change, ellipticals grow, lenticulars emerge. The story remains dynamic, Nothing stays exactly the same forever. If galaxies could attend a family reunion, irregular galaxies would almost certainly be the relatives everyone kept staring at. Not because they were the largest, not because they were the brightest, but because they seemed determined to ignore all the rules everyone else was following. Spiral galaxies organize themselves into elegant disks and sweeping arms. Elliptical galaxies settle into smooth, rounded structures. Lenticular galaxies occupy the middle ground between the two. Then there are irregular galaxies. Look at one through a telescope and you may find yourself asking a perfectly reasonable question. What exactly am I looking at? There's no obvious symmetry, no graceful spiral pattern, no smooth elliptical glow. Instead, irregular galaxies often appear chaotic. Bright star clusters scatter across uneven regions. Gas clouds stretch in unusual directions. Dust lanes twist through seemingly random locations. Some look distorted. Others appear fragmented. A few resemble cosmic accidents frozen in time, and yet despite their strange appearances, irregular galaxies are among the most important galaxies in the universe. In many cases, they reveal what happens when gravity, collisions, star formation, and cosmic history refuse to produce something neat and orderly. They're reminders that nature does not always care about our classification systems. Sometimes the universe simply does its own thing. To understand irregular galaxies, it's helpful to start with an important point. The word irregular does not mean unimportant, nor does it mean temporary. It simply means the galaxy lacks the obvious structure seen in spirals and ellipticals. Astronomers created the category because certain galaxies stubbornly resisted fitting anywhere else. When early observers began classifying galaxies, most objects fell into recognizable groups. Some were spirals, some were ellipticals, others occupied intermediate positions. But then there were galaxies that seemed determined to complicate matters. No matter how researchers examined them, they refused to conform. Eventually, astronomers accepted the obvious solution: create another category. Thus, irregular galaxies became an official part of galactic classification. At first glance, this may sound like a catch-all category, a place to put anything confusing. In reality, irregular galaxies often share important characteristics. Many contain enormous quantities of gas. Many actively form stars. Many have experienced interactions with neighbouring galaxies. Many appear younger in some respects than their more organised counterparts. And perhaps most importantly, many provide clues about conditions that were more common in the early universe. Let's begin with one of the most famous galaxies ever observed, the Large Magellanic Cloud. Usually abbreviated as the LMC, this galaxy orbits the Milky Way and remains visible from the southern hemisphere without a telescope. For countless generations, people observed it long before understanding what it actually was. Today we know that the Large Magellanic Cloud is an irregular galaxy located roughly 163,000 light-years away. In galactic terms, that's practically next door. The LMC contains billions of stars, not as many as the Milky Way, not nearly as many as giant ellipticals, but still an enormous population. Its appearance immediately stands out. There's no obvious spiral structure, no clean symmetry. Instead, the galaxy contains bright star-forming regions scattered across a highly irregular shape. One of those regions is particularly remarkable, the Tarantula Nebula. This immense stellar nursery is one of the most active star-forming environments in the local group of galaxies. If the Tarantula Nebula were located at the same distance as the famous Orion Nebula, it would dominate Earth's night sky. The structure is so energetic that it almost feels excessive. Massive stars form there in huge numbers. Radiation floods the surrounding region. Powerful stellar winds reshape nearby gas clouds. The Tarantula Nebula demonstrates something important about irregular galaxies. Many remain extremely productive. They're still actively building stars, still evolving, still changing. Another nearby example is the Small Magellanic Cloud. The SMC, as astronomers usually call it, accompanies its larger companion around the Milky Way. Located roughly 200,000 light-years from Earth, it appears even more chaotic than the Large Magellanic Cloud. Its structure seems stretched and distorted. The reason becomes clear when astronomers examine its history. The Small Magellanic Cloud has spent billions of years interacting not only with the Milky Way, but also with the Large Magellanic Cloud. Gravity has pulled and twisted both galaxies repeatedly. The result is a complex shape reflecting countless past encounters. In many ways, the Magellanic Clouds provide an ideal introduction to irregular galaxies. They're close enough for detailed study, they're clearly irregular, and they reveal how gravitational interactions can reshape entire galaxies. This idea turns out to be crucial. Many irregular galaxies are irregular because something happened to them. Not always, but often. Galaxies do not exist in complete isolation. They interact, they merge, they pass near one another, they exchange material. Over immense timescales, those encounters leave visible marks. Imagine two cities connected by rivers. Over centuries, trade, migration and development gradually alter both places. Now imagine replacing centuries with billions of years and rivers with gravity. The principle becomes surprisingly similar. Interactions change galaxies. Some changes are subtle, others are dramatic. Irregular galaxies frequently preserve evidence of those transformations. One particularly striking example is NGC 4449. Located roughly 12 million light-years away, NGC 4449 appears chaotic and energetic. Astronomers classify it as a starburst galaxy, as well as an irregular galaxy. That means it forms stars at an unusually high rate. Observations reveal streams of stars and evidence of past interactions with smaller neighbouring systems. The galaxy's present appearance reflects a long history of gravitational encounters. It's messy, complicated, and scientifically fascinating. Looking at NGC 4449, one gets the sense that galaxies can have turbulent lives. Not every system evolves quietly over billions of years. Some experience repeated disruptions, some undergo bursts of activity, some seem permanently unwilling to settle down. Irregular galaxies often belong to that category. One reason these galaxies attract so much attention is their gas content. Many contain large reservoirs of hydrogen. That's important because hydrogen serves as the primary raw material for star formation. When sufficient gas accumulates, gravity can trigger collapse. Stars begin forming, clusters emerge, entire stellar populations appear. As a result, irregular galaxies frequently contain bright blue regions filled with young stars. These regions stand out dramatically against the surrounding structure. In fact, some irregular galaxies appear almost patchy. Bright clusters scattered across uneven backgrounds. The effect can make them look unfinished, as though the galaxy is still under construction. In a sense, that's exactly what's happening. Galaxies are never truly finished, but irregular systems often make that reality easier to see. Another fascinating aspect of irregular galaxies involves their size. Most are smaller than major spirals and giant ellipticals, not all, but many. This fact has led astronomers to consider an intriguing possibility. Perhaps irregular galaxies preserve characteristics similar to those of ancient galaxies that existed earlier in cosmic history. When researchers observe extremely distant galaxies, they're looking backward in time. Some of the earliest galaxies appear surprisingly irregular, clumpy, chaotic, poorly organised. The modern irregular galaxies we observe nearby may offer hints about those ancient conditions. They're not identical, of course. Billions of years separate them, yet certain similarities remain. This connection makes irregular galaxies valuable windows into the past. By studying them, astronomers gain insights into how galaxies may have behaved when the universe was much younger. And the early universe was a busy place. Galaxies were closer together. Interactions occurred more frequently. Mergers were common. The orderly structures we associate with mature galaxies had not fully emerged. In that environment, irregularity may have been more normal than exception. Today's elegant spirals and giant ellipticals represent the outcomes of billions of years of evolution. Irregular galaxies remind us that those outcomes were not guaranteed. Order had to develop. Structure had to emerge. The process took time. Interestingly, not all irregular galaxies look alike. Astronomers often divide them into subcategories. Some show hints of structure. Others appear completely chaotic. A few seem distorted by recent interactions. Others may simply lack enough mass to develop stable spiral patterns. Again, nature provides multiple pathways to similar results. One galaxy may become irregular because of a collision, another because of gravitational interactions, another because it never developed a stable disk in the first place. The final appearance can look surprisingly similar despite very different histories. That complexity keeps astronomers busy. Every irregular galaxy presents a puzzle. What happened here? What forces shape this structure? How long has the galaxy looked this way? Will it eventually evolve into something more organized? Or will it remain irregular for billions of years to come? The answers vary from one object to another, and that's part of the appeal. Irregular galaxies refuse to become predictable. The role of dark matter adds another layer of intrigue. Observations indicate that many irregular galaxies contain significant amounts of dark matter. In some cases, the invisible component may dominate the galaxy's total mass. Stars and gas provide only part of the picture. The hidden gravitational framework remains essential. Without it, many irregular galaxies might not survive at all. This realization highlights an important theme throughout modern astronomy. What we see is often only a fraction of what's actually there. The visible universe tells part of the story. Gravity reveals the rest. One particularly surprising fact is how resilient some irregular galaxies can be. Despite their chaotic appearances, many remain stable for immense periods of time. They may look disorganized from our perspective, yet they continue existing successfully across billions of years. Apparently, the universe does not require perfect symmetry to function. Nature tolerates a remarkable amount of variation, perhaps more than humans sometimes expect. The study of irregular galaxies has also influenced our understanding of star formation itself. Because many of these galaxies actively produce stars, they provide excellent laboratories for observing the process in action. Astronomers can examine giant molecular clouds, observe young stellar populations, study how radiation affects surrounding gas, investigate how massive stars reshape their environments. The lessons learned extend far beyond irregular galaxies alone. They help explain stellar evolution throughout the universe. And that's really the remarkable thing about these seemingly chaotic systems. At first glance, they appear messy, disordered, difficult to classify. Yet the more closely astronomers examine them, the more valuable they become. They reveal galactic interactions, preserve clues about cosmic history, demonstrate ongoing star formation, provide insight into dark matter, and offer glimpses of conditions that may once have been widespread throughout the universe. In short, irregular galaxies are not mistakes. They're not failed spirals. They're not incomplete ellipticals. They're simply another way for a galaxy to exist. A reminder that nature values diversity far more than tidy categories. And while many irregular galaxies contain billions of stars, they are still relatively modest compared to another group. Because once astronomers began counting galaxies, they discovered something surprising. The universe contains vast numbers of galaxies that are even smaller. At first glance, dwarf galaxies don't sound particularly impressive. The name certainly doesn't help. When people hear the word dwarf, they naturally imagine something minor, something small enough to sit quietly in the background while larger and more dramatic objects receive all the attention. In astronomy, however, size can be misleading, very misleading. Dwarf galaxies may be smaller than giant spirals and massive ellipticals, but they are among the most important structures in the universe. In fact, there's a good argument that without dwarf galaxies, many of the larger galaxies we've already discussed might never have existed at all. And perhaps the most surprising fact is this. Dwarf galaxies may be the most common type of galaxy in the entire cosmos, not the spirals, not the giant ellipticals, not the spectacular merging systems photographed by famous space telescopes. Dwarf galaxies. Tiny systems containing millions or billions of stars rather than hundreds of billions or trillions. The universe appears to be absolutely full of them. To appreciate just how common they are, let's begin with our own galactic neighbourhood. The Milky Way does not travel through space alone. Surrounding it are dozens of smaller companion galaxies. Some orbit quietly in the darkness, others are gradually being pulled apart by gravity. A few are currently merging with our galaxy. Many of these companions are dwarf galaxies. In fact, if you could somehow view the Milky Way from far outside, you wouldn't just see a single galaxy, you would see an entire system, a giant spiral galaxy surrounded by numerous smaller satellites. Rather like a large city surrounded by towns and villages, and this pattern repeats throughout the universe. Large galaxies often possess swarms of smaller companions. For many years, astronomers underestimated how important these dwarf systems were. They were difficult to detect. Most are faint. Many contain relatively few stars. Some are almost invisible compared to the galaxies around them. Then observations improved. More dwarf galaxies were discovered, then more, then even more. Eventually, researchers realized something remarkable. Dwarf galaxies aren't exceptions. They're everywhere. One reason dwarf galaxies are so fascinating is that they come in many varieties. Some resemble miniature ellipticals. Others look irregular and chaotic. A few contain active star-forming regions. Others appear ancient and quiet. The category dwarf galaxy describes size rather than shape. This means dwarf galaxies can follow many different evolutionary paths. Nature, as usual, prefers variety. Let's start with one of the most famous examples, the Sagittarius dwarf spheroidal galaxy. This galaxy provides a dramatic demonstration of what can happen when a dwarf ventures too close to a giant. Located relatively near the Milky Way, the Sagittarius dwarf has spent billions of years orbiting our galaxy. Unfortunately for the dwarf galaxy, the Milky Way's gravity is incredibly powerful. As a result, the Sagittarius dwarf is being torn apart. Stars are gradually being stripped away. Long streams of stellar material stretch across the sky. Eventually, the galaxy will likely disappear entirely as a distinct object. Its stars will become part of the Milky Way. In a sense, we are watching galactic evolution in action, not quickly, not dramatically, but steadily. The process resembles a slow-motion merger unfolding over immense spans of time. Another famous example is the Fornax dwarf galaxy. This small galaxy orbits the Milky Way at a distance of roughly 460,000 light-years. Despite its modest size, Fornax contains several globular clusters and a surprisingly rich history. Astronomers have discovered multiple generations of stars inside it. Some are extremely old, others formed much later. This suggests that even relatively small galaxies can experience long and complicated evolutionary journeys. The story becomes even more interesting when we consider the Draco dwarf galaxy. At first glance, Draco seems almost unimpressive. It's faint, small, difficult to observe. Yet measurements suggest it contains enormous amounts of dark matter. In fact, dark matter may outweigh its visible stars by a tremendous margin. Imagine looking at a galaxy and realizing most of its mass is invisible. That's exactly what astronomers have found. Draco has become one of the most important laboratories for studying dark matter because of this. Sometimes the smallest galaxies teach the biggest lessons. The relationship between dwarf galaxies and dark matter is one of the most fascinating topics in modern astronomy. Evidence suggests that many dwarf galaxies are heavily dominated by dark matter. In some cases, the visible stars represent only a tiny fraction of the total mass. This makes dwarf galaxies valuable tools for investigating one of science's greatest mysteries. Astronomers cannot see dark matter directly, but they can observe its effects. Stars move faster than expected. Galaxies remain stable when they shouldn't. Gravitational influences reveal hidden mass. Dwarf galaxies often provide especially clear examples of these phenomena, and because they're relatively simple systems, researchers can study them with fewer complications than massive galaxies. It's rather like learning how an engine works by examining a small machine before moving on to a giant industrial factory. The fundamental principles become easier to isolate. Another reason dwarf galaxies matter is their role in galactic construction. Current theories suggest that many large galaxies grew partly through the accumulation of smaller ones. The early universe contained numerous small structures. Gravity gradually brought them together. Collisions occurred, mergers followed, larger galaxies emerged. This means dwarf galaxies may represent some of the building blocks from which giant galaxies were assembled. The Milky Way itself provides evidence for this idea. Astronomers have discovered stellar streams throughout our galaxy. These streams consist of stars that once belonged to smaller galaxies. Over billions of years, those galaxies were absorbed. Their stars survived. The original structures did not. In a sense, the Milky Way contains pieces of ancient dwarf galaxies woven throughout its own history. Every large galaxy may carry similar traces. The giants did not appear fully formed. They grew. They evolved. And dwarf galaxies played an important role in that process. One particularly famous dwarf galaxy is the Leo 1 dwarf galaxy. This small system orbits far from the Milky Way centre and has provided important clues about the mass of our galaxy. By tracking its motion, astronomers can estimate how much dark matter surrounds the Milky Way. It's an excellent example of how dwarf galaxies can help scientists understand larger structures. Sometimes the smallest companions reveal the most important information. Not all dwarf galaxies are quiet. Some are surprisingly active. Consider the IC10. This galaxy is experiencing a period of intense star formation. Massive stars are being born at unusually high rates. Powerful stellar winds and radiation flood the surrounding regions. Despite its relatively small size, IC10 behaves like a cosmic construction zone. The activity demonstrates that dwarf galaxies are fully capable of dramatic events. Size does not necessarily determine excitement. A small galaxy can be every bit as energetic as a much larger one, sometimes more so. The variety among dwarf galaxies has led astronomers to create several subcategories: dwarf spheroidals, dwarf ellipticals, dwarf irregulars, ultra-faint dwarfs. Each group possesses distinct characteristics. Some contain almost no gas. Others remain rich in hydrogen. Some actively form stars. Others stopped billions of years ago. The diversity is remarkable. In fact, two dwarf galaxies may differ more from one another than some giant galaxies do. One especially intriguing category involves ultra-faint dwarf galaxies. These systems push the definition of a galaxy almost to its limit. Some contain only a few thousand visible stars. That's tiny by galactic standards. A large globular cluster may contain more stars. Yet measurements reveal something important. The stars are embedded within dark matter halos. That distinction separates them from ordinary star clusters. They're genuine galaxies. Just extraordinarily small ones. The discovery of ultra-faint dwarfs has transformed our understanding of galactic populations. For decades, astronomers suspected many small galaxies remained undiscovered. Recent surveys confirmed that suspicion. As observational techniques improved, new dwarf galaxies appeared regularly. Many are so faint that detecting them requires sophisticated analysis. And there may still be numerous examples waiting to be found. One challenge in studying dwarf galaxies involves survival. Life is difficult when you're small and surrounded by giants. Large galaxies exert powerful gravitational forces, gas can be stripped away, stars can be pulled outward, entire structures can be disrupted. Over billions of years, many dwarf galaxies are absorbed by larger systems. This process has occurred repeatedly throughout cosmic history. Some dwarf galaxies survive by remaining distant. Others survive through fortunate orbital paths. Many do not survive at all. The universe can be an unforgiving place. Yet despite these challenges, dwarf galaxies continue to exist in vast numbers, in galaxy clusters, around large spirals, and throughout intergalactic space. They're persistent, resilient, and incredibly numerous. Some astronomers have even referred to them as the hidden majority of galactic populations. That phrase captures something important. When people think about galaxies, they usually imagine the giants, the Milky Way, Andromeda, massive ellipticals. Those galaxies are spectacular. They're also relatively uncommon. Dwarf galaxies may not dominate photographs, but they dominate the numbers. If the universe conducted a census, dwarf galaxies would likely represent the largest voting bloc by far. Another fascinating aspect of dwarf galaxies involves chemical evolution. Because many contain relatively few stars, their histories can be easier to reconstruct. Astronomers analyze stellar compositions to determine when different generations formed. The results provide clues about star formation, supernova explosions, and galactic growth. In some cases, dwarf galaxies preserve ancient stellar populations dating back nearly to the beginning of cosmic history. They become archaeological sites on a galactic scale. The stars act as historical records. Every chemical signature contains information. Every observation contributes another piece to the puzzle. This connection to the early universe is particularly valuable. The first galaxies were likely much smaller than the giant systems we see today. Studying modern dwarf galaxies helps researchers understand those ancient conditions. The comparison isn't perfect. Billions of years separate them. Nevertheless, important similarities remain. Dwarf galaxies offer glimpses of what galactic life may have looked like during the universe's youth, and perhaps that's their greatest contribution. They remind us that bigger is not always more important. The universe is filled with examples where small objects play enormous roles. Tiny particles shape chemistry, small stars outlive massive ones, and dwarf galaxies help build giants. Without them, the cosmic story would look very different. They are the hidden workforce of galactic evolution, the overlooked majority, the quiet builders whose contributions extend across billions of years. Some galaxies reveal their histories immediately. You don't need complicated measurements. You don't need advanced simulations. You don't even need decades of observation. One glance is often enough. Something happened here. Something dramatic. Something powerful enough to reshape an entire galaxy. Ring galaxies belong firmly in that category. Unlike spiral galaxies with their elegant arms or elliptical galaxies with their smooth, glowing shapes, ring galaxies often look almost impossible at first sight. A bright ring of stars surrounds an emptier central region. Sometimes the structure appears astonishingly symmetrical. Sometimes it looks slightly distorted. Occasionally it resembles a giant cosmic target floating in darkness. The effect can be so striking that early observers struggled to understand what they were seeing. How does a galaxy end up looking like that? Why would billions of stars arrange themselves into a gigantic ring? And perhaps most importantly, what kind of event could leave behind such an extraordinary structure? The answer turns out to involve one of the most spectacular processes in the universe, a galactic collision. Not the sort of collision usually depicted in science fiction. Not stars crashing directly into one another. Not planets exploding. The reality is both slower and more fascinating. Ring galaxies are often the frozen fingerprints of encounters that unfolded across millions of years. They preserve evidence of cosmic impacts long after the original event occurred. In a sense, they're enormous astronomical crime scenes. The collision happened long ago, the evidence remains, and astronomers act as detectives trying to reconstruct what took place. To appreciate how unusual ring galaxies are, It helps to remember how galaxies normally evolve. Most galaxies spend billions of years changing gradually. Gravity reshapes structures. Stars form and die. Gas clouds move through the system. Mergers occur occasionally. Yet despite all these processes, recognizable galactic forms often survive. Spiral galaxies generally remain spirals. Ellipticals remain ellipticals. Changes occur, but they often happen slowly. Ring galaxies tell a different story. They announce that something significant interrupted normal evolution. Imagine dropping a pebble into a still pond. The impact generates waves. Those waves spread outward from the centre. The water itself remains present, but its distribution changes. For a brief period, a circular pattern dominates the surface. Now replace the pond with a galaxy. Replace the pebble with another galaxy. Replace the water with billions of stars, gas clouds, and dark matter. The comparison isn't perfect, but it's surprisingly close to what can happen. When a smaller galaxy passes directly through the disk of a larger galaxy, gravitational forces generate a powerful density wave. That wave moves outward. Stars respond. Gas responds. Matter becomes compressed into expanding rings. The result can be a ring galaxy, a gigantic ripple frozen in space. One of the most famous examples is undoubtedly the Cartwheel Galaxy. If ring galaxies have a celebrity, the Cartwheel Galaxy is probably it. Located roughly 500 million light-years away, the Cartwheel Galaxy immediately captures attention. A brilliant ring surrounds the central region. Spokes appear to connect different parts of the structure. The entire galaxy resembles an enormous wheel suspended in the darkness, hence the name. For decades, astronomers have studied the Cartwheel Galaxy as one of the best examples of collision-driven galactic evolution. Current evidence suggests that a smaller galaxy passed through the centre of a larger spiral galaxy long ago. The resulting gravitational disturbance generated an outward-moving wave. As that wave travelled through the galaxy, it compressed gas clouds. Star formation increased dramatically. Massive young stars appeared throughout the expanding ring. Today, those bright stellar populations continue illuminating the structure. Looking at the Cartwheel Galaxy is almost like viewing a cosmic explosion in slow motion. Not an explosion driven by energy, an explosion driven by gravity. Another fascinating example is Hoag's Object. Hoag's Object remains one of the strangest galaxies ever discovered. Unlike the Cartwheel Galaxy, which clearly displays evidence of collision-related complexity, Hoag's Object appears almost unnervingly perfect. A nearly circular ring of young blue stars surrounds a bright yellow central core. Between them lies a relatively empty region. The geometry is so precise that astronomers initially wondered whether the object might represent an entirely different phenomenon. Even today, Hoag's Object continues to generate discussion. Its formation history remains somewhat mysterious. Several explanations have been proposed. Perhaps it formed through an ancient interaction. Perhaps internal processes shaped the ring. Perhaps a long-forgotten merger played a role. The answer remains uncertain. Astronomy occasionally encounters objects that refuse to provide easy explanations. Hoag's Object belongs in that category, and that's part of what makes it famous. Then there is AM0644-741, another remarkable example of the class. This galaxy displays a spectacular ring filled with active star formation. Observations reveal enormous clusters of young stars scattered throughout the structure. The ring itself spans tens of thousands of light-years. Once again, evidence points toward a galactic encounter as the likely trigger. A smaller galaxy passed through the larger system. Gravity did the rest. One of the most surprising things about ring galaxies is how rare they are. Considering the number of galaxies in the universe, ring galaxies represent only a tiny fraction of the population. That rarity makes sense. The conditions required to create a prominent ring are quite specific. The collision must occur along the right trajectory. The timing must be favourable. The galaxies involved must possess suitable structures. Not every encounter produces a ring. Many collisions generate other outcomes. Some create tidal tails, some trigger mergers, some distort spiral arms. Only certain interactions generate the spectacular rings we observe. As a result, ring galaxies often attract enormous scientific interest. They're unusual enough to provide special insights into galactic dynamics. One particularly important feature of ring galaxies involves star formation. The outward-moving density wave compresses gas as it travels. Compressed gas tends to form stars. This means many ring galaxies contain intense star-forming regions concentrated along the ring itself. In some cases, the ring becomes one of the most active stellar nurseries in the entire galaxy. Bright blue stars appear, massive stellar clusters form, radiation floods surrounding regions. The ring effectively becomes a moving wave of galactic construction. As the wave expands, star formation follows. This process helps explain the colours astronomers observe. Many ring galaxies display vivid blue rings surrounding older, redder central regions. The colour contrast reflects different stellar populations. Young stars dominate the ring, older stars dominate the core. The visual result can be spectacular, yet the beauty also tells a scientific story. Colours become evidence. Evidence becomes history. History becomes understanding. Another fascinating aspect of ring galaxies is that they allow astronomers to study gravitational physics on enormous scales. The structure itself acts almost like a natural experiment. Researchers can analyse how stars respond to disturbances, how gas behaves under compression, how density waves propagate through galactic disks. Each observation improves our understanding of galactic evolution. Ring galaxies may be rare, but they teach valuable lessons. Sometimes unusual objects provide the clearest insights. Astronomy has a long history of learning from exceptions. The objects that don't fit expectations often reveal the most. Ring galaxies certainly qualify. Of course, not every ring galaxy forms through the same mechanism. Nature rarely restricts itself to one solution. While many ring galaxies originate through collisions, others may arise through internal processes. Resonances associated with bars can sometimes produce ring-like structures. Gravitational interactions can create partial rings. Complex evolutionary histories can generate features resembling rings without direct impacts. The universe is remarkably creative. Astronomers must carefully analyse each galaxy individually. The appearance alone does not always tell the entire story. That challenge keeps the field interesting. Every ring galaxy becomes an investigation. What happened here? When did it happen? How fast is the ring expanding? Which galaxy was responsible? Is the structure temporary or long-lasting? Answering these questions often requires observations across multiple wavelengths. Visible light reveals stars, infrared observations reveal dust. Radio observations reveal hydrogen gas. X-ray observations reveal energetic processes. Each wavelength contributes another piece of evidence. Together they reconstruct events that occurred hundreds of millions of years ago. It's an extraordinary achievement when you think about it. Human beings living on a small planet around an ordinary star can analyse collisions that occurred hundreds of millions of light years away and hundreds of millions of years in the past. That's not something our ancestors could have imagined. Yet modern astronomy does it routinely. The existence of ring galaxies also reminds us that galaxies are not isolated islands. They're participants in a larger cosmic community. Gravity constantly links objects together. Galaxies influence one another. They interact. They merge. They collide. The consequences can persist for billions of years. A ring galaxy represents one visible consequence, a record written across tens of thousands of light years. In some ways, these galaxies serve as cosmic photographs, not photographs of a single instant, photographs of a process. The ring captures a particular stage of evolution. Given enough time, the structure will change, the ring will expand, star formation will evolve, the galaxy will continue its journey. Eventually, the dramatic appearance may fade. Future observers might never guess what happened. Fortunately, we happen to exist during an era when many ring galaxies remain visible. We can study them, learn from them, admire them, and appreciate the extraordinary forces capable of reshaping entire galaxies. One especially interesting realization emerged as astronomers studied larger populations of galaxies. Collisions are not unusual, they're actually quite common throughout cosmic history. The Cartwheel galaxy and its relatives simply preserve especially obvious evidence. Many galaxies have experienced encounters, many are experiencing them now, and many will continue experiencing them in the future. Not every galaxy is content to create stars at a slow and steady pace. For most galaxies, star formation resembles a long-term investment. Gas clouds collapse gradually. New stars appear continuously. The process unfolds across millions or billions of years. The galaxy remains productive, but relatively measured in its approach. Then there are starburst galaxies. These galaxies seem to throw moderation out the window. Instead of forming stars at ordinary rates, they experience periods of extraordinary activity. Massive stellar nurseries ignite throughout the galaxy. Enormous quantities of gas collapse into new stars. Regions that would normally take hundreds of millions of years to develop may become intensely active in a much shorter period. It's as though the galaxy suddenly decides to conduct thousands of years of construction projects all at once. The result can be spectacular. Bright clusters of young stars appear throughout the galaxy. Powerful radiation floods surrounding space. Supernova explosions become more frequent. The entire system enters a period of rapid transformation. Astronomers call this phenomenon a starburst, and while the term sounds dramatic, it turns out to be remarkably accurate. A starburst galaxy is not simply a galaxy that forms stars. Nearly all galaxies do that to some degree. A true starburst galaxy forms stars at rates far above normal expectations, sometimes 10 times faster, sometimes dozens of times faster, occasionally even more. The pace becomes so extreme that the galaxy cannot sustain it indefinitely. That's one of the most important characteristics of a starburst. It's temporary. A galaxy can maintain ordinary star formation for billions of years. A major starburst consumes fuel much more rapidly. Eventually, the available gas begins running low. The frenzy subsides. The galaxy settles into a quieter state. In that sense, a starburst galaxy represents a special moment in a much longer story. We're observing the system during one of its busiest periods, a period of intense growth and dramatic change. The obvious question, of course, is why this happens. What causes a galaxy to suddenly accelerate star formation? As astronomers investigated starburst galaxies, a clear pattern began emerging. Many of them showed evidence of interactions with other galaxies. Not all, but many. The connection appears again and again throughout the universe. Galaxies approach one another. Gravity begins reshaping both systems. Gas clouds become compressed. Material is funneled into dense regions. Star formation increases. Sometimes it increases enormously. A galactic encounter acts like a catalyst. Conditions that previously existed in relative balance become disturbed. The result is a burst of stellar creation. Imagine a calm forest where seeds germinate gradually over time. Then imagine a series of events suddenly creating ideal growing conditions everywhere at once. Growth accelerates dramatically. The galaxy experiences something similar. The raw materials were already present. The interaction changes how those materials behave. One of the most famous examples of a starburst galaxy is Messier 82. Astronomers often refer to it as M82, or the Cigar Galaxy. Located roughly 12 million light-years away, M82 provides one of the best opportunities to study starburst activity in detail. At first glance, the galaxy appears unusual. Its shape looks elongated. Its structure seems disturbed. Observations quickly reveal why. M82 has been strongly influenced by interactions with its larger neighbour, Messier 81. The gravitational encounter between these galaxies dramatically altered conditions inside M82. Huge quantities of gas became concentrated in central regions. Star formation surged. Today, M82 produces stars at a rate many times greater than the Milky Way. The consequences are visible across multiple wavelengths. Young stars flood the galaxy with radiation. Powerful stellar winds blow material outward. Supernova explosions occur frequently. Observations reveal enormous streams of gas extending above and below the galactic disk. The galaxy almost seems to be venting excess energy into surrounding space. Looking at images of M82, one gets the impression of a galaxy working overtime, and in many ways that's exactly what's happening. Another remarkable example is NGC 253. The Sculptor galaxy ranks among the brightest galaxies visible from Earth and has become one of astronomy's most studied starburst systems. Located approximately 11 million light-years away, NGC 253 contains active regions where stars form at unusually high rates. Infrared observations reveal enormous quantities of dust and gas. Radio observations reveal complex structures. X-ray observations reveal energetic activity associated with young stellar populations. The galaxy serves as a reminder that starbursts are not confined to one particular galactic type. Various galaxies can experience them under the right circumstances. The key ingredient is often the concentration of gas. Where sufficient fuel gathers, star formation follows, sometimes quietly, sometimes spectacularly. A third famous example is NGC 3310. This galaxy displays clear evidence of past interactions and mergers. Its structure appears disturbed. Bright regions of star formation spread across the system. Astronomers believe a collision with another galaxy helped trigger the starburst. The event dramatically reshaped the galaxy's appearance and accelerated stellar production. Observing NGC 3310 is almost like viewing the aftermath of a cosmic construction boom. Everywhere researchers look, they find evidence of recent activity. Young stars, dense gas clouds, regions undergoing rapid transformation. The relationship between starbursts and galactic collisions has become one of the most important themes in modern astronomy. When galaxies interact, gravity does far more than distort shapes. It rearranges matter. Gas clouds that once occupied stable orbits may begin moving inward. Material accumulates near the centre. Compression increases. Conditions become favourable for star formation. And because galaxies contain enormous amounts of gas, the resulting activity can be extraordinary. The scales involved are difficult to comprehend. A single giant molecular cloud may contain enough material to create millions of stars. Entire populations of stellar clusters can emerge during a starburst. Massive stars appear in large numbers. These stars burn brightly, they live briefly, and they die dramatically. This creates another fascinating aspect of starburst galaxies. Their evolution proceeds rapidly. The newly formed massive stars release huge amounts of energy. Radiation affects nearby gas. Stellar winds reshape surrounding regions. Eventually, supernova explosions inject additional energy into the environment. The galaxy experiences a cascade of consequences. One generation of stars influences the next. The effects spread throughout the system. In some cases, astronomers observe enormous outflows known as galactic winds. These winds are not winds in the everyday sense. No atmosphere is involved. Instead, they're streams of gas driven outward by intense stellar activity. Thousands or even millions of stars collectively inject energy into the surrounding environment. The pressure becomes sufficient to push material away from the galaxy. M82 provides one of the most famous examples. Observations reveal giant plumes of gas extending far beyond the visible disk. The starburst is literally reshaping the galaxy's surroundings. It's a remarkable demonstration of how stars influence the larger structures around them. For many years, astronomers wondered whether starbursts played an important role in the early universe. Evidence increasingly suggests they did. The young universe was a crowded place. Galaxies existed closer together. Interactions occurred more frequently. Mergers were common. Conditions favourable for starbursts may have been widespread. In other words, what appears exceptional today may once have been relatively normal. Some distant galaxies observed by modern telescopes exhibit star formation rates far beyond anything seen in the Milky Way. These observations help researchers understand how galaxies grew during cosmic history. Rapid stellar production may have contributed significantly to the development of many large systems. Without starbursts, galactic evolution might have proceeded very differently. Another interesting feature of starburst galaxies involves chemical enrichment. Every generation of stars produces heavier elements. When stars die, especially in supernova explosions, those elements return to the surrounding environment. Future stars incorporate that material. Over time, galaxies become chemically richer. Starburst galaxies accelerate this process. Large numbers of stars form and die within relatively short periods. The cycle speeds up. Chemical evolution proceeds more rapidly. Elements essential for planets, moons, and eventually life become more abundant. In a sense, starbursts help manufacture the raw ingredients required for future cosmic structures. It's an impressive contribution for something that begins as a cloud of gas collapsing under gravity. Not all starbursts involve entire galaxies. Sometimes the activity concentrates in central regions. Sometimes it spreads throughout the disk. The details vary from system to system. Astronomers continue studying these differences to better understand what controls star formation. The answers remain complex. Gas density matters. Galactic interactions matter. Magnetic fields may contribute. Dark matter influences overall structure. Supermassive black holes can sometimes affect conditions as well. Nature rarely relies on a single factor. Instead, multiple processes work together. The result is the extraordinary diversity observed throughout the universe. One especially intriguing question concerns the future of starburst galaxies. What happens when the burst ends? The answer depends on circumstances. Some galaxies eventually return to more ordinary rates of star formation. Others may exhaust much of their available gas. Still, others continue evolving through additional interactions and mergers. The starburst represents a phase rather than a permanent identity. A galaxy experiencing intense activity today may look very different a billion years from now. This theme appears repeatedly throughout astronomy. Galaxies are not fixed objects. They evolve, they transform, they respond to their environments. Categories help us understand them, but the underlying reality remains dynamic. And perhaps that's what makes starburst galaxies so compelling. They're snapshots of change happening at extraordinary scales, places where the universe becomes unusually productive, where stars appear in great numbers, where gravity, gas, and time combine to create some of the most active environments known. Most galaxies shine because of their stars. That statement sounds almost too obvious to mention. Stars produce light. Galaxies contain stars. Therefore galaxies shine. Simple. For the overwhelming majority of galaxies in the universe, that's essentially the whole story. Even giant elliptical galaxies containing trillions of stars derive their brightness primarily from stellar populations. Starburst galaxies become exceptionally luminous because they create huge numbers of new stars. Spiral galaxies glow because billions of stars illuminate their disks. The stars do the work. Then astronomers discovered something strange. Some galaxies appeared far too bright. Not slightly brighter, not moderately brighter, absurdly brighter. The amount of energy pouring from their centres seemed almost impossible. In some cases, a tiny central region produced more light than the rest of the galaxy combined. In other cases, the central source outshone the entire host galaxy altogether. At first, nobody knew what to make of these observations. The brightness seemed unreasonable. What kind of object could generate so much energy? What mechanism could power such extraordinary luminosity? The answer eventually led astronomers toward one of the most remarkable discoveries in modern science: supermassive black holes, not merely as passive objects sitting quietly at galactic centres, not merely as cosmic curiosities, but as engines capable of producing some of the most energetic phenomena in the universe. And when those engines become active, the resulting galaxies enter a category known as active galaxies. To understand active galaxies, it's helpful to begin with a misconception. Black holes themselves do not emit light. A black hole is black. The clue is in the name. The brightness comes from material surrounding the black hole. Gas and dust falling inward form a structure called an accretion disk. As matter spirals toward the event horizon, it becomes compressed and heated. Temperatures rise dramatically. The material begins emitting enormous amounts of radiation. The process becomes astonishingly efficient. In fact, matter falling into a supermassive black hole can convert energy more efficiently than nuclear fusion inside stars. The result is extraordinary brightness. And because supermassive black holes reside at the centres of most large galaxies, the potential exists almost everywhere. The key difference is activity. Many galactic black holes are relatively quiet. Others are feeding, and when they feed, entire galaxies can transform. One of the most famous active galaxies is Messier 87. We've encountered M87 before as a giant elliptical galaxy. Its central black hole became famous after the first direct image of a black hole was obtained. But M87 offers another remarkable feature: a gigantic jet of material extending thousands of light years into space. This jet originates near the supermassive black hole. Magnetic fields and energetic particles combine to create one of the most spectacular structures observed in astronomy. The jet is so large that it remains visible across enormous distances. Looking at images of M87, it's difficult not to be impressed. The galaxy contains trillions of stars, yet one of its most striking features originates from a region far smaller than the galaxy itself. Another famous example is Centaurus A, also known by its catalogue designation NGC 5128. Centaurus A ranks among the closest active galaxies to Earth. Located roughly 13 million light-years away, it appears unusual even before examining its active nucleus. A dark dust lane cuts across the galaxy's centre. The structure hints at a complicated history involving mergers and interactions. Radio observations reveal enormous lobes extending far beyond the visible galaxy. These structures span hundreds of thousands of light-years. The energy responsible ultimately originates from activity near the central supermassive black hole. Centaurus A demonstrates how active galactic nuclei can influence regions vastly larger than the black hole itself. The effects spread across enormous scales. Another celebrated active galaxy is NGC 1068, also known as Messier 77. NGC 1068 became one of the defining examples of a Seyfert galaxy. Seyfert galaxies represent a major class of active galaxies characterized by extremely bright galactic centers. Observations of NGC 1068 helped astronomers develop many of the ideas that now underpin active galaxy research. The galaxy's nucleus produces tremendous radiation across multiple wavelengths: visible light, infrared light, X-rays, radio emissions. The central engine affects nearly every observation astronomers make. Then there is NGC 4151. Astronomers sometimes refer to NGC 4151 as one of the most intensively studied active galaxies in the sky. Because it's relatively nearby, researchers have spent decades examining its central region. The galaxy provides valuable insights into how supermassive black holes interact with surrounding material. Its activity varies over time. Brightness changes occur, gas flows evolve. The galaxy serves as a natural laboratory for understanding active galactic nuclei. The story becomes even more dramatic when we arrive at quasars. If active galaxies are energetic, quasars operate on an entirely different level. The word quasar originally came from quasi-stellar radio source. Early observers detected unusual radio-emitting objects that looked star-like through telescopes. The mystery deepened when astronomers analysed their spectra. The objects turned out to be astonishingly distant and astonishingly bright, much brighter than anyone expected. Today we understand that quasars are among the most luminous objects in the universe. They're powered by supermassive black holes, actively consuming enormous quantities of matter. The surrounding accretion disks release staggering amounts of energy. In some cases, a quasar can outshine hundreds of billions of stars. Imagine a single galactic nucleus producing more light than an entire galaxy. That's the scale we're discussing. One of the most famous quasars ever discovered is 3C273. Located billions of light years away, 3C273 became historically important because it was the first quasar whose nature was correctly understood. Its discovery fundamentally changed astronomy. Suddenly, researchers realized that the universe contained objects of extraordinary power. Even today, 3C273 remains one of the brightest quasars visible from Earth. It continues serving as a benchmark for active galaxy research. Another famous example is 3C48. This object played a crucial role during the early investigation of quasars. Its unusual properties puzzled astronomers for years. Eventually, it became clear that 3C48 represented another example of a distant active galactic nucleus. Like many scientific breakthroughs, understanding arrived gradually. Evidence accumulated. Ideas evolved. The mystery slowly unravelled. Then we have PKS 0637-752. This quasar attracted attention because of its spectacular jet structure. Observations revealed energetic material extending across enormous distances. The object provided valuable insights into how jets form and propagate through space. Once again, a central black hole influences regions vastly larger than itself. The scale difference remains astonishing. A black hole smaller than the solar system can affect structures spanning thousands of light years. Another remarkable quasar is APM 8279+5255. For a time, it ranked among the most luminous objects known. The energy output is difficult to comprehend. Numbers quickly become absurd, trillions of times brighter than the sun. When astronomers encounter objects like this, ordinary intuition becomes almost useless. The scales involved belong entirely to the cosmos. One especially famous modern example is TON 618. TON 618 contains one of the largest known black holes ever discovered. Estimates place its mass at tens of billions of times the mass of the Sun. The quasar's luminosity is equally impressive. TON 618 has become something of a celebrity among astronomy enthusiasts because it combines two extraordinary features: extreme brightness, extreme size. Either would be remarkable. Together they create one of the most impressive known objects in the observable universe. Another well-known quasar is ULA SJ1342+0928. What makes this object special isn't merely its brightness, it's its age. Or more accurately, the age of the universe when its light was emitted. This quasar existed when the universe was less than 1 billion years old. Its discovery forced astronomers to confront important questions. How did supermassive black holes grow so quickly? How did such powerful objects emerge so early? The answers remain active areas of research. Every new observation adds another piece to the puzzle. Then there is JO313-1806, discovered in the distant universe. JO 313-1806 hosts a massive black hole at an unexpectedly early cosmic epoch. Its existence challenges certain models of black hole growth. Once again, the universe demonstrates a talent for surprising astronomers. Just when a theory appears comfortable, a new observation arrives. Another famous category of active galaxies involves blazars. These objects become particularly bright because one of their jets points almost directly toward Earth. The orientation dramatically increases apparent brightness. One of the most famous examples is BL Lacertae. BL Lacertae became so important that an entire class of objects was named after it. Observations reveal rapid brightness variations and powerful emissions across multiple wavelengths. The galaxy's orientation plays a crucial role in what we observe. This highlights an important lesson. Sometimes the appearance of an active galaxy depends not only on its physical properties, but also on our viewing angle. Astronomers now believe many different active galaxy categories may share similar underlying structures. The differences often arise from perspective. Imagine observing the same city from different directions. One observer sees skyscrapers, another sees suburbs, another sees industrial districts. The city remains the same, the viewpoint changes. Something similar occurs with active galaxies. Orientation influences observations. This realization helped unify many seemingly different phenomena. At the center sits a supermassive black hole. Around it lies an accretion disk. Jets may emerge. Dust and gas surround the system. Viewing angle determines which features dominate. The unified model became one of the major achievements of active galaxy research. Of course, active phases do not last forever. Eventually fuel supplies change, gas becomes depleted, activity declines. The galaxy settles into a quieter state. This means active galaxies represent phases rather than permanent categories. A galaxy active today may become relatively calm in the future. A quiet galaxy may have been active in the distant past. The Milky Way itself likely experienced more active periods earlier in its history. Even now, evidence suggests our central black hole was more energetic millions of years ago than it is today. Galaxies evolve, black holes evolve, the story continues. Perhaps the most remarkable thing about active galaxies and quasars is what they reveal about energy. Stars seem powerful, and they are. Yet under the right circumstances, matter falling toward a black hole can release even greater amounts of energy. The brightest quasars become visible across billions of light years. Their light began travelling long before Earth looked the way it does today. Yet we can still detect it, still study it, still learn from it. They function like cosmic lighthouses, not because they guide travellers, but because they illuminate distant eras of cosmic history. After spending time with quasars and active galaxies, it might seem difficult for the universe to become any more energetic. We've already encountered supermassive black holes capable of outshining entire galaxies. We've explored objects visible across billions of light years. We've watched matter fall toward black holes and release extraordinary amounts of energy. Surely that's dramatic enough for one category of galaxies. Then astronomers began listening to the universe instead of simply looking at it. And suddenly an entirely different picture emerged. Not every galaxy announces its presence through visible light alone. Some galaxies broadcast enormous amounts of energy at radio wavelengths. In fact, certain galaxies produce radio emissions so powerful that they can be detected across vast cosmic distances. These systems became known as radio galaxies. And among the most spectacular examples, the visible galaxy itself turns out to be only a small part of the story. The truly astonishing structures exist far beyond what ordinary telescopes can see. Enormous radio-emitting lobes stretch across hundreds of thousands or even millions of light years. Jets of energetic particles blast outward from galactic centers. The scale becomes so large that the galaxy almost seems secondary to the structures surrounding it. Radio galaxies are not merely galaxies, they're broadcasting systems operating across intergalactic space. To understand why radio galaxies are so remarkable, we should begin with a simple question. What exactly is radio astronomy? When most people imagine astronomy, they think about visible light, telescopes gathering faint starlight, photographs showing colourful nebulae and galaxies. But visible light represents only a small portion of the electromagnetic spectrum. The universe also produces radio waves, infrared radiation, ultraviolet light, X-rays, gamma rays. Each wavelength reveals different information. If visible light astronomy is like looking at the universe, radio astronomy is like listening to it. And when radio telescopes began surveying the sky during the 20th century, astronomers discovered sources of radio emission far stronger than expected. Some originated within our own galaxy. Others came from far beyond. Many of the most powerful sources turned out to be active galaxies. The connection was not immediately obvious. Visible observations often showed ordinary-looking galaxies. Radio observations revealed gigantic structures extending far outside them. It was as though someone discovered that a quiet-looking town was secretly operating one of the largest broadcasting stations on Earth. The visible appearance told only part of the story. One of the first and most famous radio galaxies ever identified is Cygnus A. Cygnus A transformed astronomy. Located roughly 760 million light-years away, it ranks among the strongest radio sources in the sky. Through ordinary telescopes, the host galaxy appears relatively modest. Through radio telescopes, the picture changes dramatically. Enormous lobes of radio emission extend outward from the galaxy. Jets connect these lobes to the central region. The entire structure spans hundreds of thousands of light-years. Cygnus A became one of the key objects that helped astronomers understand how active galaxies generate radio emissions. Even today, it remains one of the most studied radio galaxies in existence. The basic mechanism involves the same central engine we've already encountered, a supermassive black hole. Material falls inward, an accretion disk forms, energy is released. But in some galaxies, the process also generates powerful jets. These jets consist of charged particles accelerated to enormous speeds. Magnetic fields help guide and shape them. The particles stream outward from the galactic center, sometimes for hundreds of thousands of light-years, sometimes for millions. As the jets interact with surrounding environments, they create vast radio-emitting structures. The resulting lobes can become far larger than the visible galaxy itself. One remarkable example is Centaurus A. We've already encountered Centaurus A as an active galaxy. It also happens to be one of the nearest major radio galaxies. Visible light observations reveal a striking galaxy crossed by a dark dust lane. Radio observations reveal something much larger. Huge lobes extend far beyond the visible structure. These lobes stretch hundreds of thousands of light-years into space. The energy required to create them is extraordinary. Yet the source remains a relatively small central region, surrounding a supermassive black hole. This contrast never stops being impressive. A central engine smaller than the solar system can influence structures larger than entire galaxies. Another famous example is Messier 87. M87 seems determined to appear in every discussion involving supermassive black holes, and for good reason. The galaxy hosts one of the most famous black holes ever studied. It also possesses a spectacular relativistic jet. Visible observations reveal the jet extending from the galaxy's center. Radio observations show even more extensive structures. The galaxy serves as a perfect illustration of how black holes can affect their environments across enormous distances. Astronomers have spent decades studying M87 because it offers insights into jet formation, black hole physics, and radio galaxy evolution. The lessons learned there apply throughout the universe. As observations improved, researchers began realizing that radio galaxies come in different forms. Some produce relatively modest radio structures, others generate truly gigantic systems. One famous classification divides radio galaxies into two major categories, FR1 and FR2. The names come from astronomers Bernard Phaneroff and Julia Riley, who recognised important differences between radio galaxy structures. FR1 galaxies tend to have jets that gradually fade with distance. FR2 galaxies display bright hotspots near the outer edges of their radio lobes. The distinction may seem technical, but it reflects differences in energy output and environmental interactions. Once again, nature reveals complexity beneath apparent simplicity. One particularly spectacular FR2 radio galaxy is Picta A. Picta A contains a jet extending hundreds of thousands of light years. Observations across multiple wavelengths have revealed extraordinary details about its structure. The galaxy has become one of the most important objects for understanding how energetic particles travel through space. When researchers study radio galaxies, they are often studying particle acceleration, under conditions impossible to recreate on Earth. The universe provides laboratories far larger than anything humans could build. Then there is Hercules A. This galaxy possesses some of the most impressive radio lobes ever observed. The structures extend far beyond the visible galaxy. Looking at radio images of Hercules A feels almost surreal. The central galaxy appears tiny compared to the surrounding emissions. It's as though the radio structures have become the dominant feature, while the galaxy itself merely hosts the engine responsible. Another remarkable example is 3C236. This object belongs to a special category known as giant radio galaxies. Its radio structures span more than 15 million light-years. To appreciate that number, remember that the Milky Way is roughly 100,000 light-years across. The radio emissions associated with 3C236 extend across distances vastly larger than typical galaxies. The scale becomes difficult to visualize. Entire groups of galaxies could fit within the structure. And yet the source remains a supermassive black hole operating at the galaxy's center. The universe seems unusually fond of connecting tiny origins with enormous consequences. Radio galaxies also reveal something important about galactic environments. The jets do not travel through empty space, they move through intergalactic gas. As they interact with that material, they transfer energy. The process can influence star formation. It can alter gas distributions. It can affect neighbouring structures. In some cases, radio jets may actually suppress star formation by heating surrounding gas. This creates an intriguing paradox. The same black hole capable of powering extraordinary activity may also help prevent future stellar growth. Astronomers refer to this process as feedback. The galaxy influences the black hole. The black hole influences the galaxy. Both evolve together. Neither operates in isolation. This realization transformed our understanding of galactic evolution. For many years, researchers treated black holes and galaxies as separate subjects. Today it's clear that they're deeply connected. One particularly fascinating radio galaxy is NGC 4261. Observations have revealed a prominent disk of material surrounding its central black hole. The galaxy provides valuable evidence about how accretion processes work. It also demonstrates the close relationship between black hole activity and radio emissions. Every well-studied radio galaxy seems to contribute another piece to the puzzle. Another famous object is 3C31. Its jets have been mapped in extraordinary detail. Researchers use galaxies like 3C31 to study how relativistic jets evolve as they move through surrounding environments. The structures often appear smooth near the center, but become increasingly complex farther out. The changes reveal valuable information about interactions with intergalactic matter. Radio astronomy turns invisible processes into observable science. One of the most extraordinary aspects of radio galaxies involves timescales. The jets and lobes we observe today often required millions of years to develop. Some structures preserve evidence of activity that occurred long ago. In certain cases, astronomers find galaxies where radio emissions suggest multiple periods of activity. The central engine switched on, then quieted, then became active again. The galaxy's radio structures preserve a record of those cycles. Like tree rings recording environmental history, radio lobes preserve evidence of past behavior. The universe leaves clues everywhere. The challenge lies in learning how to read them. Radio galaxies have also helped astronomers investigate cosmic magnetic fields. The jets contain charged particles. Charged particles respond to magnetic fields. By studying radio emissions, researchers can map structures otherwise impossible to observe directly. This provides insights into environments stretching across millions of light years. Few other astronomical tools offer similar opportunities. Another reason radio galaxies matter is their role in galaxy clusters. Many of the most powerful examples reside within dense galactic environments. Their jets inject energy into surrounding gas. That energy influences cluster evolution. In some cases, radioactivity prevents gas from cooling efficiently. This affects future star formation throughout entire regions. A single active galaxy can influence an enormous cosmic neighborhood. The consequences extend far beyond the host galaxy itself, and perhaps that's what makes radio galaxies so remarkable. At first glance, they seem like another variety of active galaxy. Look more closely, and they reveal themselves as some of the largest structures associated with individual galaxies anywhere in the universe. Jets stretching across intergalactic space, lobes spanning millions of light years. Energy outputs capable of reshaping environments on enormous scales. They're not merely galaxies emitting radio waves, they're giant broadcasting systems powered by supermassive black holes. Imagine standing on a distant planet and looking up at a night sky that changes dramatically over the course of millions of years. At first, a neighbouring galaxy appears as a faint smudge of light, a beautiful but distant object. Then, very slowly, almost imperceptibly, it grows larger. The glow becomes brighter. Its shape becomes clearer. Its stars seem to stretch across a greater portion of the sky. Millions of years pass. The galaxy continues approaching. Eventually it dominates the heavens. Its spiral arms span enormous distances overhead. The night sky no longer belongs to one galaxy. It belongs to two. And then the real transformation begins. Gravity starts pulling at both systems. Stars shift their orbits. Gas clouds collide. Long streams of stars stretch into space. Entire galactic structures begin changing shape. The collision has begun. Not the kind of collision people usually imagine. No deafening impact, no explosion, no sudden destruction. Galactic collisions are among the slowest dramatic events in the universe. They're cosmic encounters unfolding across hundreds of millions or even billions of years. Yet despite their slow pace, they rank among the most powerful transformative processes known to astronomy. Entire galaxies can be reshaped. Star formation can surge. Black holes can become active. New galaxies can emerge. And throughout cosmic history, these interactions have played a central role in building the universe we see today. One of the first surprises many people encounter when learning about galactic collisions is this: stars almost never collide. At first, that seems impossible. How can two galaxies containing billions or even trillions of stars pass through one another without widespread stellar impacts? The answer lies in distance. Galaxies may appear crowded in photographs, but the spaces between stars are enormous. Extraordinarily enormous. If our sun were reduced to the size of a tennis ball, the nearest star would still be hundreds of kilometers away. The stars inside galaxies are separated by vast regions of emptiness. When galaxies merge, most stars simply pass by one another. Their orbits change. Their paths become distorted, but direct collisions remain extremely rare. It's a bit like throwing two clouds of mosquitoes through each other. The clouds interact. The individual insects rarely crash. The comparison isn't perfect, but it captures the basic idea. The real action occurs elsewhere. Gas clouds collide. gravity rearranges structures, dark matter halos interact, star formation changes, black holes respond, the galaxies evolve, and because galaxies contain enormous amounts of gas, those changes can be spectacular. One of the most famous examples in astronomy is the antennae galaxies. If you've ever seen an image of colliding galaxies in a textbook, there's a good chance you've seen the antennae. Located roughly 45 million light-years away, these two galaxies are actively merging. Long tidal tails extend outward into space. Bright star-forming regions appear throughout the system. The original spiral structures have become heavily distorted. Looking at the antennae galaxies is like viewing a cosmic dance midway through a performance. The galaxies haven't fully merged yet. Neither remains unchanged. They're caught in transition. And because the interaction is still underway, astronomers can observe the process directly. The tidal tails are particularly fascinating. These enormous streams of stars and gas stretch far beyond the main galaxies. Gravity literally pulls material outward during the encounter. The structures can extend hundreds of thousands of light-years. In some cases, the tails contain enough material to form entirely new dwarf galaxies. A collision doesn't simply destroy, it creates. That's one of the recurring themes in galactic evolution. Transformation often produces new opportunities, new structures, new generations of stars. Another famous example is the mice galaxies. Their nickname comes from their appearance. Each galaxy possesses a long tidal tail resembling a mouse's tail. The effect is both charming and scientifically valuable. Observations suggest that the galaxies pass near one another and experience strong gravitational interactions. The encounter pulled stars and gas outward, producing the distinctive shapes visible today. Computer simulations have successfully recreated many of these features. Researchers can essentially rewind the event. By modelling the galaxy's motions, they reconstruct the collision history. It's a remarkable achievement. Imagine determining the details of an event that began hundreds of millions of years ago and spans hundreds of thousands of light-years. Modern astronomy does exactly that. Then there's NGC 7252. This galaxy represents a later stage of the merger process. Unlike the antennae, where two distinct galaxies remain visible, NGC 7252 appears much closer to becoming a single object. The original galaxies have largely blended together, yet evidence of the collision remains visible. Long tidal structures extend outward. Star clusters formed during the merger remain present. The galaxy provides a glimpse into what happens after a major collision progresses toward completion. It's effectively a preview of the future. And speaking of the future, our own galaxy has an appointment scheduled. Not tomorrow, not next year, not even next million years, but eventually. The Andromeda Galaxy is moving toward the Milky Way. The collision is expected to occur roughly 4 to 5 billion years from now. For decades, people describe this event as a galactic crash. The term isn't entirely wrong, but it can be misleading. The process will unfold slowly, very slowly. The galaxies will pass through one another. Gravity will distort both structures. Long tidal streams will form. Star formation may increase. Over time, repeated interactions will occur. Eventually, the two galaxies will merge into a single larger system. Astronomers sometimes jokingly refer to the future result as Milky Way, not an official scientific term, but a memorable one. What's especially interesting is that the Sun will likely survive the merger. Earth's fate is less certain for unrelated reasons involving the future evolution of the Sun itself. But the stars themselves are unlikely to collide. The night sky, however, would become extraordinary. Future observers would witness one of the most spectacular astronomical displays imaginable. A neighbouring galaxy growing larger and larger across the heavens. As researchers studied galactic mergers, they realised these events help explain many features observed throughout the universe. Elliptical galaxies, for example. We've already discussed how many giant ellipticals may form through mergers between spiral galaxies. The evidence supporting this idea is substantial. Computer simulations repeatedly produce elliptical-like structures following major mergers. Observations reveal galaxies at intermediate stages. The pieces fit together remarkably well. Two spirals merge. Their organized disks become disrupted. Stellar motions become more randomized. The resulting system resembles an elliptical galaxy. This process may have occurred countless times throughout cosmic history. In some cases, repeated mergers create truly enormous galaxies. The giant ellipticals found at the centers of galaxy clusters likely grew through multiple collisions and acquisitions over billions of years. One galaxy absorbs another, then another, then another. Gradually, the structure becomes larger and more massive. Galactic growth often resembles a long history of mergers, a cosmic version of expansion through acquisition. Interactions don't always lead to complete mergers. Sometimes galaxies merely pass near one another. Even these near misses can have significant consequences. A close encounter may trigger star formation, distort spiral arms, redistribute gas, activate central black holes. The galaxies continue their separate journeys afterward, but neither remains exactly the same. Gravity leaves its mark. One particularly famous example involves Messier 51. The Whirlpool galaxy's magnificent spiral structure may be partly enhanced by interactions with a smaller companion galaxy. The encounter helps shape the visible pattern. Without the interaction, the galaxy might look very different. This highlights an important point. Some of the most beautiful galaxies in the universe owe their appearance to gravitational encounters. Collisions and interactions aren't merely destructive forces, they can create extraordinary structures. The relationship between mergers and star formation is especially important. When galaxies collide, gas clouds become compressed, dense regions form, star formation accelerates. In some cases, enormous starbursts occur. We've already explored starburst galaxies, and many of them owe their activity to mergers. The connection appears repeatedly across observations. Galaxies interact, gas becomes concentrated, stars form rapidly. The galaxy enters a period of intense growth. One famous merger-driven starburst system is ARP 220. ARP 220 represents the aftermath of a major galactic merger. The collision triggered extraordinary star formation and immense infrared emissions. The system has become one of the most studied examples of merger-induced activity. Observations reveal complex structures hidden beneath thick dust. The galaxy demonstrates how collisions can radically alter galactic evolution. Mergers also influence supermassive black holes. When two galaxies combine, their central black holes eventually approach one another. Over time, they may form a binary system. Eventually, they merge. The resulting event releases enormous amounts of energy in the form of gravitational waves. Modern observatories are beginning to detect such phenomena. This means galactic mergers contribute not only to visible structures, but also to the gravitational wave universe. The consequences extend across multiple branches of astronomy. Another fascinating aspect involves timescales. Human beings often think in years, perhaps decades. Civilizations think in centuries. Galactic mergers think in billions of years. The antennae galaxies have been interacting for hundreds of millions of years. The Milky Way Andromeda merger will unfold over billions. These events remind us just how vast cosmic timescales can be. And yet, despite their duration, astronomers can reconstruct them. Computer simulations allow researchers to model interactions from beginning to end. By comparing simulations with observations, they determine likely histories. The results consistently reveal the importance of mergers. Without them, the universe would look dramatically different. Many galaxies would never have reached their current sizes. Many ellipticals would not exist. Many starbursts would never have occurred. Many black holes would have evolved differently. Galactic collisions are not rare accidents. They're fundamental components of cosmic evolution, and perhaps that's the most remarkable realization. When people first learn about galaxies, They often imagine isolated islands drifting quietly through space. The reality is much more dynamic. Galaxies interact, influence one another, exchange material, merge, grow, transform. The universe is not a collection of disconnected objects. It's a network of relationships governed by gravity. Every interaction contributes to a larger story. Every merger leaves behind evidence. Every collision helps shape the future. Try a small thought experiment for a moment. Imagine shrinking the Milky Way until it becomes the size of a coin. Not a large coin, just an ordinary one resting on a table. Now place the Andromeda Galaxy nearby, then add the Triangulum Galaxy, then dozens of dwarf galaxies. Already you've created something larger than a single galaxy. You've created a group. Keep going. Add hundreds more galaxies, then thousands. Spread them across the table. Soon the scale becomes difficult to manage. And here's the surprising part. Even that enormous collection would represent only a tiny fraction of the universe's true structure. For much of human history, simply discovering that galaxies existed beyond the Milky Way seemed revolutionary. Then astronomers realized galaxies weren't scattered randomly through space. They gathered together, they formed communities. Those communities formed larger communities. Those larger communities connected into enormous structures stretching across hundreds of millions of light years. Eventually, researchers discovered something astonishing. The universe possesses a kind of large-scale architecture. Not a design, not a blueprint, but a recognizable structure created by gravity over billions of years. And when viewed on the larger scales, the universe begins to resemble something unexpected. A web. A vast cosmic web connecting galaxies across unimaginable distances. To appreciate how extraordinary this is, let's begin with the smallest level of galactic organization beyond individual galaxies themselves: galaxy groups. The Milky Way belongs to one. Astronomers call it the local group. The local group contains more than 50 known galaxies. The exact number continues increasing as new dwarf galaxies are discovered. Most of these members are relatively small. Dwarf galaxies dominate the population. The largest members include the Milky Way, the Andromeda Galaxy, and the Triangulum Galaxy. Everything else is considerably smaller. The local group spans roughly 10 million light-years. That sounds enormous, because it is. Yet on cosmic scales, it's actually a modest structure. A small galactic neighborhood, a local community. The Milky Way and Andromeda dominate this neighborhood. Their combined gravity influences many smaller members. Over billions of years, interactions have shaped the group's history. Dwarf galaxies have been absorbed. Others continue orbiting. The story remains ongoing, and eventually the future merger between the Milky Way and Andromeda will dramatically alter the local group itself. Galaxy groups are common throughout the universe. Many galaxies spend their lives in similar environments, a handful of large galaxies surrounded by smaller companions. Gravity holds everything together. Yet groups represent only the beginning. Move outward in scale and something much larger appears. Galaxy clusters. A galaxy cluster is exactly what the name suggests, a massive collection of galaxies bound together by gravity. Not dozens, hundreds, sometimes thousands. The distances involved become enormous. One famous example is the Virgo cluster. Located roughly 55 million light-years away, the Virgo cluster contains well over 1,000 galaxies. Some estimates suggest several thousand members. This cluster dominates our region of the universe. In fact, the local group itself is moving under the gravitational influence of Virgo. That's a remarkable thing to consider. The Milky Way is not simply travelling through space independently. It participates in a larger gravitational environment. We're members of a group. The group exists within a larger region. Everything influences everything else. The Virgo cluster contains an extraordinary variety of galaxies: giant ellipticals, spiral galaxies, lenticular systems, dwarf galaxies, active galaxies. The cluster acts almost like a galactic ecosystem. different populations coexist within the same enormous structure. One particularly famous member is Messier 87. We've encountered M87 several times already. That's hardly surprising. It's one of the most impressive galaxies known. At the centre of M87 lies a supermassive black hole containing billions of solar masses. The galaxy itself contains trillions of stars, and yet even M87 is merely one member of a much larger cluster. That perspective helps illustrate the immense scales involved. Even giant galaxies become components of larger systems. Clusters possess another fascinating feature. Most of their mass is invisible. This discovery transformed astronomy. When researchers measured the motions of galaxies inside clusters, something didn't add up. The visible galaxies alone couldn't provide enough gravity. The clusters should have fallen apart. Yet they remained intact. The conclusion became unavoidable. Something else was present. Something massive, something invisible. Dark matter. Galaxy clusters provided some of the earliest and strongest evidence for its existence. In fact, the astronomer Fritz Zwicky reached this conclusion while studying the Coma cluster during the 1930s. The galaxies moved too quickly. Visible matter wasn't enough. Additional mass had to exist. At the time, the idea seemed radical. Today, dark matter has become one of the central concepts in modern cosmology. The Coma cluster remains one of the most famous galaxy clusters ever studied. Containing thousands of galaxies, it serves as a powerful example of a large-scale structure. Observations revealed giant elliptical galaxies dominating the centre. Smaller galaxies populate surrounding regions. Dark matter influences everything. The cluster itself spans millions of light years. It's less a collection of galaxies than an entire galactic city. Actually, city might be too small a word. Perhaps galactic continent is more appropriate. And yet clusters contain more than galaxies. They also contain enormous quantities of hot gas. This gas fills the space between galaxies. Temperatures reach millions of degrees. At such temperatures, the gas emits X-rays. Modern observatories can detect these emissions directly. The result is remarkable. When astronomers observe clusters in X-rays, they discover that much of the ordinary matter doesn't reside inside galaxies at all. It exists between them. The spaces we imagine as empty turn out to contain enormous amounts of material. The universe continually reminds us that emptiness is often less empty than it appears. One particularly important example is the Bullet cluster. The Bullet cluster became famous because it provided dramatic evidence for dark matter. This system consists of two galaxy clusters that collided. During the collision, the hot gas interacted strongly and slowed down. The dark matter behaved differently. By studying the separation between visible matter and gravitational effects, astronomers obtained some of the strongest evidence that dark matter exists as a real physical component of the universe. The Bullet cluster became one of cosmology's most important laboratories. Sometimes the universe performs experiments on scales humans could never create. We simply observe the results. Now let's zoom out even farther, beyond galaxy groups, beyond galaxy clusters, beyond structures millions of light years across. At this point, astronomers began noticing something even more extraordinary. Clusters themselves are not randomly distributed. They gather together. They form larger associations known as superclusters. One famous example is the Virgo supercluster. For many years, astronomers considered our region of space part of the Virgo supercluster. Then observations improved, the picture became more detailed, and researchers discovered something larger. Much larger. The structure became known as Laniakea supercluster. The name comes from Hawaiian and roughly translates to immense heaven, a fitting description. Laniakea spans more than 500 million light years. It contains approximately 100,000 galaxies. The Milky Way occupies a tiny corner. The local group forms a small component. The Virgo cluster contributes to the larger whole. Everything becomes connected. Suddenly, the universe starts feeling less like isolated islands and more like an interconnected landscape. And yet even superclusters are not the final level of organisation. The truly astonishing discovery emerged when astronomers mapped enormous regions of the universe. Instead of finding random distributions, they discovered patterns. Galaxies gather along filaments, clusters sit at intersections, vast empty regions separate them. The resulting structure resembles a gigantic web, the cosmic web. One of the most beautiful and surprising discoveries in modern science. Imagine a three-dimensional spiderweb stretching across the observable universe. Not literally, of course. The comparison simply helps visualize the pattern. Galaxies concentrate along enormous strands. These strands connect clusters and superclusters. Between them lie enormous empty regions known as cosmic voids. The largest voids span hundreds of millions of light-years, regions containing remarkably few galaxies. The contrast is extraordinary. Some areas teem with galaxies, others contain almost none. The universe becomes a landscape of filaments and voids, density and emptiness, structure and space. Gravity created this architecture over billions of years. Small fluctuations in the early universe gradually grew. Matter accumulated, filaments formed, galaxies emerged, clusters developed, the web expanded. Everything we observe today traces back to tiny differences present shortly after the universe began. That realization is almost difficult to comprehend. The largest structures in existence emerge from incredibly small beginnings. One famous filamentary structure is the Sloan Great Wall. Discovered through galaxy surveys, the Sloan Great Wall stretches across more than 1 billion light-years. At the time of its discovery, it ranked among the largest known structures in the universe. The sheer scale is difficult to visualize. Light itself requires over 1 billion years to cross it. Another remarkable example is the Hercules Corona Borealis Great Wall. This structure may extend across several billion light-years. The dimensions are so vast that they challenge intuition entirely. Human language struggles with scales like these. Numbers lose meaning. Distances become abstractions. Yet these structures exist. They're real components of the observable universe, and they reveal just how immense cosmic architecture can become. Meanwhile, between these giant structures lie enormous voids. One famous example is the Bootes Void. The Bootes Void spans hundreds of millions of light-years. Compared to surrounding regions, it contains very few galaxies. If galaxy-rich regions resemble cities, the Bootes Void resembles a vast cosmic desert. Not completely empty, just extraordinarily sparse. These voids are just as important as the filaments themselves. Together they define the universe's large-scale structure. Without voids, there would be no web. Without the web, galaxies would not gather the way they do. Everything connects. The cosmic web also helps explain galactic evolution. Galaxies located inside dense regions experience more interactions, more mergers, more environmental effects. Galaxies inside less crowded regions often evolve differently. Location matters. The neighbourhood influences the future. Just as environments shape cities, environments shape galaxies. And perhaps that's the most remarkable lesson from this enormous journey outward. We began with individual galaxies, spirals, ellipticals, lenticulars, irregulars, dwarfs, ring galaxies, starbursts, active galaxies, radio galaxies, merging systems. Each seemed impressive on its own, yet every one of them exists within something larger. Groups, clusters, superclusters, filaments, the cosmic web itself. The deeper astronomers looked, the more connected everything became. Galaxies are not isolated objects scattered randomly through darkness. They're participants in a vast cosmic network spanning the observable universe. What do all these galaxy types, structures, interactions, and environments ultimately tell us about the history of the universe itself? Long before astronomers understood what galaxies actually were, people naturally assumed the stars they could see represented most of the universe. The assumption made sense. Look up at the night sky, and that's what appears to be there. Stars, thousands of them. Perhaps a faint band of light stretching across the darkness. Maybe a planet or two. Nothing about that view immediately suggests hundreds of billions of galaxies. Nothing suggests structures spanning millions of light years. Nothing hints at an enormous cosmic web connecting regions separated by distances so vast that human language struggles to describe them. And yet, that is precisely what the universe contains. Over the course of our journey, we've travelled through spiral galaxies, barred spirals, ellipticals, lenticulars, irregular galaxies, dwarf systems, ring galaxies, starbursts, active galaxies, radio galaxies, mergers, clusters, and superclusters. At first, these categories may have seemed like separate topics, different boxes, different labels, different kinds of galaxies. But once astronomers began understanding how these objects relate to one another, a much larger picture emerged. The categories were never the main story. The story was evolution. Because galaxy types are not merely classifications, they're evidence. Evidence of where galaxies came from, evidence of what they've experienced, evidence of how the universe itself has changed across nearly 14 billion years of cosmic history. In a sense, every galaxy functions like a historical document. Not a document written with words, a document written with stars. A spiral galaxy tells one story. A giant elliptical tells another. An irregular galaxy reveals something different. Together they form a record of the universe's life story, and perhaps the most remarkable thing about that story is that it was not obvious from the beginning. If you had travelled back billions of years into the past, the universe would have looked very different. The elegant spiral galaxies we admire today were not always present. The giant ellipticals dominating galaxy clusters did not begin in their modern form. The immense cosmic structures spanning hundreds of millions of light years had not fully emerged. Everything was younger, smaller, less organised. The universe was still building itself. Modern telescopes have allowed astronomers to witness portions of that process. Not because anyone can travel through time, because light itself acts as a record. When we observe a galaxy 1 billion light years away, we see it as it existed 1 billion years ago. When we observe a galaxy 10 billion light years away, we see it as it existed 10 billion years ago. The farther we look, the farther back in time we travel. The universe provides its own archive. And what that archive reveals is fascinating. The earliest galaxies often look strange, chaotic, irregular, clumpy. Many lack the elegant structures common today. This observation immediately suggests something important. Galaxies evolved. The orderly systems we observe now emerged gradually. They were not present from the beginning. This brings us back to irregular galaxies. For a long time, irregular galaxies seemed like odd exceptions, galaxies that somehow failed to become spirals or ellipticals. Today, astronomers view them differently. In many ways, irregular galaxies may offer glimpses of earlier stages in galactic evolution. Not identical copies of ancient galaxies, of course. Billions of years separate them, but they preserve characteristics that help researchers understand the universe's youth. Their chaotic appearances hint at a time when order had not yet fully emerged, a time when galaxies were still assembling themselves. Dwarf galaxies tell a related story. Throughout our exploration, we repeatedly encountered the idea that larger galaxies grow by absorbing smaller ones. Evidence for this process appears everywhere. The Milky Way contains remnants of ancient dwarf galaxies. Andromeda contains them as well. Giant ellipticals show evidence of repeated mergers. The implication is profound. Many of the largest galaxies in existence began as smaller systems. They grew. They merged. They accumulated mass. The giants of today were once much more modest. This idea fundamentally changed astronomy. Galaxies were no longer viewed as static islands floating through space. They became evolving systems with histories histories that could be reconstructed, histories written across billions of years. Spiral galaxies contribute another crucial piece of the puzzle. When people think of galaxies, spirals often come to mind first: the Milky Way, Andromeda, the Whirlpool Galaxy. Their graceful structures seem almost timeless. Yet spirals are not permanent. They're stages, moments within longer evolutionary stories. Some spirals may eventually become lenticular galaxies. Others may merge with neighbouring galaxies. Still others may experience periods of intense activity driven by interactions. The existence of spiral galaxies reveals that the universe contains environments where long-term stability can emerge. Billions of stars can organise themselves into coherent structures lasting immense periods of time. Gravity, operating patiently over billions of years, creates order. That lesson appears repeatedly throughout cosmic history. Then there are barred spiral galaxies. At first glance, the difference between a spiral and a barred spiral may seem minor, a structural variation, an architectural detail. Yet bars reveal something important about internal evolution. Galaxies are not only influenced by external forces, they change from within. Material flows inward. Stars alter their orbits. Gas redistributes itself. The galaxy evolves even in relative isolation. This realization expanded scientific understanding. Evolution did not require collisions alone. Internal processes mattered too. The universe turned out to be more dynamic than previously imagined. Lenticular galaxies strengthen this picture. They occupy a fascinating middle ground, part spiral, part elliptical, neither fully one nor the other. Their existence suggests transitions, transformations, the possibility that galaxies can migrate between categories over time. Rather than fixed identities, galaxy types become stages within larger narratives. This shift in perspective may be one of astronomy's most important achievements. Classification remains useful, but classification alone is not the goal. Understanding change is the goal. Understanding how one state becomes another. Understanding how cosmic history unfolds. Elliptical galaxies reveal what happens when evolution proceeds for extraordinary lengths of time. Many giant ellipticals contain ancient stellar populations. The majority of their stars formed billions of years ago. Some sit at the centres of galaxy clusters, having grown through repeated mergers and acquisitions. They're not simply large galaxies. They're survivors, records of countless interactions accumulated over cosmic history. When astronomers study giant ellipticals, they're often studying the outcomes of long evolutionary journeys. The galaxies preserve evidence of events stretching back almost to the beginning of the universe itself. Ring galaxies tell a different story, a story of interruption, a story of collisions. The existence of ring galaxies reminds us that evolution is not always gradual. Sometimes dramatic events reshape galaxies quickly, at least quickly by cosmic standards. A collision generates a density wave, star formation erupts, the galaxy changes appearance, the event becomes visible across hundreds of thousands of light years. Ring galaxies demonstrate that interactions can leave enormous fingerprints on galactic history. The same lesson appears even more clearly in merging galaxies, the antennae galaxies, the mice galaxies, NGC7252, countless others. These systems reveal the universe in motion. Not motion occurring over minutes or hours, motion occurring over millions and billions of years, entire galaxies approaching one another, passing through one another, combining, transforming, creating something new. For much of scientific history, galaxies were treated as isolated objects. Modern observations shattered that idea. Galaxies interact constantly. The universe is far more social than early astronomers realized. Starburst galaxies extend this story. Their existence demonstrates how interactions influence star formation. When galaxies merge, gas clouds become compressed. Star formation accelerates. Entire populations of stars appear. The consequences ripple outward through future generations. Chemical enrichment increases. New stellar clusters emerge. Planet-forming materials become more abundant. A merger affects not only the galaxies involved, but potentially the future environments within them. The chain of consequences becomes enormous. One event triggers another, which triggers another. The universe evolves through interconnected processes. Active galaxies and quasars add yet another layer. For centuries, black holes were purely theoretical ideas. Then evidence accumulated. Eventually, astronomers realized that supermassive black holes occupy the centers of most large galaxies. Not only that, the black holes influence galactic evolution. They regulate gas, they generate jets, they produce radiation, they affect star formation. The relationship runs both directions. Galaxies help grow black holes help shape galaxies. Neither can be fully understood without the other. This realization transformed cosmology. Two subjects once studied separately became deeply connected. Radio galaxies reveal just how extensive those connections can become. A central black hole influences structures spanning hundreds of thousands or even millions of light years. Jets reshape surrounding environments. Energy transfers into galaxy clusters. The consequences spread far beyond the host galaxy itself. Small regions generate enormous effects. Again and again, the universe demonstrates this principle. Tiny beginnings, large consequences. The same principle appears on the larger scales. Galaxy groups grow into clusters. Clusters become parts of superclusters. Superclusters connect through the cosmic web. And suddenly the story expands beyond individual galaxies altogether. One of the most remarkable discoveries of the last century is that galaxies are not distributed randomly. Gravity organized matter into enormous structures. Filaments stretch across the universe. Clusters gather at intersections. Vast voids separate them. The resulting cosmic web spans the observable universe. This structure contains perhaps the deepest lesson of all. Everything is connected, not philosophically, physically. Galaxies influence neighboring galaxies. Groups influence clusters. Clusters influence superclusters. Dark matter shapes the entire framework. Nothing exists entirely alone. The universe is a network, a vast gravitational ecosystem extending across billions of light years. And perhaps that's the ultimate meaning hidden within galaxy classification. The categories themselves are not the destination. They're clues. Each category reveals one piece of a larger narrative. Irregular galaxies reveal youth. Dwarf galaxies reveal origins. Spirals reveal organization. Lenticulars reveal transition. Ellipticals reveal maturity. Ring galaxies reveal collisions. Starbursts reveal accelerated growth. Active galaxies reveal black hole influence. Radio galaxies reveal large-scale feedback. Mergers reveal transformation. Clusters reveal community. The cosmic web reveals connection. Taken together, they describe the life story of the universe. A universe that began remarkably simple. A universe that gradually became more complex. A universe where gravity spent billions of years turning tiny fluctuations into stars, galaxies, clusters, and structures stretching across unimaginable distances. And perhaps the most extraordinary part of that story is where it leads, because every galaxy we've discussed, every spiral arm, every elliptical giant, every radio jet, every starburst, every dwarf galaxy, every galaxy cluster, every filament of the cosmic web, exist within a universe that is still evolving. The story is not finished. Galaxies continue merging, stars continue forming, black holes continue growing, clusters continue interacting, the cosmic web continues changing. Future astronomers, whether human or something else entirely, will observe a universe different from the one we see today. The evolution continues, the narrative moves forward, and somewhere within a relatively ordinary barred spiral galaxy called the Milky Way, on a small rocky planet orbiting an ordinary yellow star. A species recently learned how to recognize all of this, to map galaxies, to classify them, to reconstruct their histories, to understand their relationships, to discover that the universe is far larger, older, and more interconnected than anyone once imagined. Not bad for a civilization that spent most of its history believing the stars above were all there was. And as the night grows quieter and the journey through galaxies comes to an end, perhaps the most comforting thought is this: the universe does not need us to understand it in order to continue its story. The galaxies will keep evolving, the clusters will keep gathering, the cosmic web will keep stretching across the darkness. Yet for a brief moment in cosmic history we get to look upward, ask questions, and piece together enough of the puzzle to see the larger picture. A picture made of spirals and ellipticals, of dwarfs and giants, of collisions and creation, of structures so vast they challenge imagination, all connected within one extraordinary universe still writing its story among the stars.